You are not real, not in the way you think you are. Right now, sitting wherever you are, feeling the weight of your body, the air moving in and out of your lungs, the absolute certainty that the world around you is solid and stable and dependable, you are experiencing an illusion, not a trick, not a metaphor, an actual, measurable, scientifically verifiable illusion that your brain constructs every single millisecond to keep you functional. Because the truth about reality, the actual nature of what exists beneath the surface of your experience, is so profoundly strange that if you could perceive it directly, you would not be able to move, eat, speak, or survive. The universe is 13.8 billion years old. It began as something smaller than an atom and exploded into everything you see today. But here is what almost no one tells you. The atoms that make up your body, the chair beneath you, the walls around you, are 99.99999% empty space. The particles that fill that space do not exist in a single location until something observes them. Space-time itself is not a stage where events happen. It is a fabric that bends, warps, and flows like water. And consciousness, the thing reading these words right now, has no agreed-upon explanation in science. No one knows where it comes from. No one knows why it exists. No one can tell you what it actually is. This is not a video about theories. This is not speculation or philosophy dressed up as science. This is a 2-hour journey through 13.8 billion years of cosmic history, quantum mechanics, relativity, neuroscience, and the hardest problem humanity has ever faced. What is real? What actually exists when you strip away every illusion your senses create? The answer is not what you expect. Before we begin, let us know in the comments below where in the world you're watching from and what time it is there. Now, settle in for a journey. Reality began 13.8 billion years ago. Not approximately, not roughly, 13.787 billion years, give or take 20 million. We know this with a precision that borders on the absurd. The universe, everything that has ever existed or ever will exist, all of it, started at a specific moment in time with a margin of error smaller than 1%. Think about that for a second. We can't agree on what happened at a family dinner last Thanksgiving. Half the people at the table will swear Uncle Jerry told the story about the boat. The other half insist it was Aunt Linda, and it wasn't even a boat, it was a jet ski. But a bunch of physicists with telescopes and equations can tell you to within 20 million years when the entire cosmos began. 20 million years sounds like a lot until you realize it represents an error bar of about 0.1% across the full span of cosmic history. That's not a guess, that's a measurement. The story starts in a place that shouldn't exist, a singularity. Not a black hole, not a point in space. Space itself didn't exist yet, neither did time. The singularity was a state of infinite density and infinite temperature compressed into a region smaller than anything you can picture, smaller than an atom, smaller than a nucleus, smaller than a quark. Some models suggest the entire observable universe, every galaxy, every star, every planet, every atom in your body, was packed into a volume smaller than a single proton. Others go further and say it might have been a true geometric point with zero size. Either way, it was a place where the rules break, where the mathematics we use to describe reality stop working and start spitting out infinities. Physicists hate infinities. An infinity in an equation is the universe's way of saying you're asking the wrong question. We don't know what caused the singularity to exist. We don't know what came before it, or if before even makes sense as a concept when time itself hasn't started yet. What we do know is that 13.8 billion years ago, something happened. the singularity began to expand, fast, unimaginably fast. In a billionth of a trillionth of a trillionth of a second, the universe grew by a factor of 10 to the 26th power. That's not a typo. 10 with 26 zeros after it. A region smaller than a subatomic particle inflated to something the size of a grapefruit, and it did it faster than the speed of light. This period is called cosmic inflation, and it's one of the most important ideas in all of cosmology. Not because it's proven beyond doubt, it isn't, but because it solves problems that the standard Big Bang model couldn't touch. Without inflation, the universe we see today doesn't make sense. The cosmic microwave background, the faint glow of radiation left over from the early universe, is almost perfectly uniform in every direction we look. The temperature variations across the entire sky are less than 1 part in 100,000. That uniformity is a problem. For two distant regions of space to have the same temperature, they need to have been in contact at some point. Heat needs time to equalize. But if you run the expansion backward without inflation, those regions were never close enough to exchange energy. They should have wildly different temperatures. The fact that they don't suggests something happened in the earliest moments to smooth everything out before the ordinary expansion began. Inflation does that. It takes a tiny patch of space, small enough that temperature can equalize, and stretches it to a size larger than the observable universe today. Problem solved. The inflationary period lasted an absurdly short amount of time. Current estimates put it somewhere between 10 to the negative 36 seconds and 10 to the negative 32 seconds. Then it stopped. The universe transitioned into a slower, more familiar kind of expansion, and all that energy driving inflation didn't just disappear. It got dumped into the fabric of space itself, reheating the universe to temperatures so high that matter as we know it couldn't exist. This is the hot Big Bang, the part most people picture when they hear the term. A fireball, a cosmic furnace, a state so extreme that the four fundamental forces we rely on today, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, hadn't fully separated yet. At the very beginning, in the first moments after inflation, physicists believe all four forces were unified into a single force. As the universe expanded and cooled, they split off one by one. Gravity peeled away first, almost immediately. Then the strong nuclear force, the glue that holds atomic nuclei together. Then the weak force, which governs radioactive decay. Finally, electromagnetism. Each separation was a phase transition, like water freezing into ice or steam condensing into liquid. The universe was changing states as it cooled, and each change left a permanent imprint on the structure of reality. About 1 second after the Big Bang, the temperature had dropped to around 10 billion degrees Celsius. That's 18 billion degrees Fahrenheit, if you prefer your cosmic infernos in different units. At that temperature, the universe was a seething soup of fundamental particles, quarks, electrons, neutrinos, photons, all of them colliding, annihilating, reforming in a chaotic dance. There were no atoms yet, no nuclei, just a hot, dense plasma where matter and energy were barely distinguishable from each other. If you could somehow take a spoonful of that early universe and bring it into a lab today, it would be the most violent, unstable substance imaginable. And it filled all of space. The first stable structures began to form in the first few minutes. As the temperature continued to drop, quarks started sticking together to form protons and neutrons. This is called the quark epoch, and it lasted only a few millionths of a second. Once protons and neutrons appeared, the universe entered a new phase called Big Bang nuclear synthesis. For a brief window, roughly 3 to 20 minutes after the initial expansion, conditions were just right for nuclear fusion. Protons and neutrons smashed together, forming the nuclei of the lightest elements. Hydrogen, which is just a single proton. Helium, with 2 protons and usually 2 neutrons. Tiny traces of lithium and beryllium. That's it, nothing heavier. The universe cooled too quickly for anything else to form. The elements that make up planets, that make up your bones, your blood, the air you breathe, none of that existed yet. Those would have to wait for stars. For the next 380,000 years, the universe was opaque. Not dark, opaque. Light existed. Photons were everywhere, bouncing around in the hot plasma like pinballs in a machine, but they couldn't travel freely. Every time a photon tried to move, it immediately collided with an electron. The universe was a fog. If you had eyes and could somehow survive in that environment, you wouldn't see anything. Not because there was no light, but because light couldn't get anywhere. It was trapped. Then the universe cooled below a critical threshold, around 3,000 degrees. That doesn't sound cool, but compared to billions of degrees, it's practically freezing. At that temperature, electrons finally slowed down enough to be captured by atomic nuclei. Protons grabbed electrons and became hydrogen atoms. Helium nuclei did the same. This moment is called recombination, which is a terrible name because the electrons and nuclei had never been combined before, but the name stuck, and the moment recombination happened, the universe changed. All those photons that had been bouncing around for hundreds of thousands of years suddenly had nothing to collide with. Atoms are electrically neutral. Photons pass right through them, so the light, all of it, was released at once. The fog cleared. The universe became transparent. That light is still traveling. It's the oldest light in the universe, and it's everywhere. It's called the cosmic microwave background, and it's the single most important piece of evidence we have for the Big Bang. When astronomers first detected it in 1965, it was an accident. 2 engineers at Bell Labs, Arno Penzias and Robert Wilson, were trying to eliminate noise from a radio antenna and kept picking up a persistent hiss from every direction in the sky. They thought it was bird droppings. They cleaned the antenna. The signal didn't go away. It wasn't noise. It was the echo of creation. Penzias and Wilson had stumbled onto the afterglow of the Big Bang itself, cooled and stretched by 13.8 billion years of cosmic expansion into faint microwave radiation. They won the Nobel Prize in 1978. The cosmic microwave background is almost perfectly uniform, but not quite. There are tiny fluctuations, hot spots and cold spots, at the level of 1 part in 100,000. Those fluctuations are the seeds of everything that came after. Regions that were slightly denser than average had a little more gravity. They pulled in more matter. Over millions of years, those tiny density differences grew into the large-scale structure of the universe. Galaxies, galaxy clusters, superclusters, vast filaments of matter stretching across hundreds of millions of light-years. All of it traced back to quantum fluctuations in the inflationary period, tiny random variations that got stretched to cosmic scales and frozen into the fabric of space. The precision with which we've mapped the cosmic microwave background is staggering. The European Space Agency's Planck satellite, which operated from 2009 to 2013, measured the temperature of the early universe across the entire sky with a resolution finer than 1/10 of a degree. The data from Planck is what gives us that 13.787 billion year figure. It's not a guess. It's a direct measurement of the geometry, density and expansion history of the universe, encoded in the pattern of light left over from when the cosmos was 380,000 years old. You can fit that data into the equations of general relativity, run them forward, and out pops the age. The uncertainty is 20 million years, across 13.8 billion. That's a rounding error by cosmological standards, But here's where it gets uncomfortable. We've measured the age with extraordinary precision, but we still don't know what most of the universe is made of. The matter we can see, stars, planets, gas, dust, all of it, makes up less than 5% of the total energy content of the cosmos. About 27% is dark matter, a substance we've never directly detected but infer from its gravitational effects. The remaining 68% is dark energy, something even stranger, an unknown force causing the expansion of the universe to accelerate. We've named these things. We've measured their effects. We have no idea what they actually are. Imagine being able to time a race to the millisecond, but not knowing what the runners are made of or why they're speeding up as they approach the finish line. That's modern cosmology. The inflationary model, as elegant as it is, raises its own set of questions. What caused inflation to start? What caused it to stop? The most popular models invoke a hypothetical field called the inflaton, but no one has detected it. No one knows what it is or how it couples to the other fields in nature, and inflation makes a prediction that's deeply weird. If inflation happened once, it probably didn't stop everywhere at once. In most versions of the theory, inflation is eternal. Some regions of space stop inflating and form universes like ours. Other regions keep going, spawning an endless cascade of pocket universes, each with potentially different physical laws. This is the multiverse, and it's not science fiction. It's a direct consequence of taking inflation seriously. Whether that idea is testable, whether it even qualifies as science in the traditional sense, is a debate that has split the physics community for decades. The early universe was also a place of symmetry breaking. The laws of physics, as we understand them, are built on symmetries, patterns that stay the same under certain transformations. Rotate a sphere, and it looks the same. Shift a pattern in time, and the physics doesn't change. But the universe we live in is not perfectly symmetric. Matter, for instance, is far more common than antimatter. In the early universe, the two should have been produced in equal amounts. Every particle should have had an antiparticle counterpart. When they met, they annihilated, producing light. If the balance had been perfect, everything would have annihilated, and the universe today would be nothing but photons. Instead, there was a tiny imbalance, about one extra matter particle for every billion matter-antimatter pairs. That tiny excess is why anything exists at all. We don't know why the imbalance was there. It's one of the deepest unsolved problems in physics. The universe had a bias, and that bias is the only reason you're here to wonder about it. So where does this leave us? 13.8 billion years ago, reality began, not in a place, not from something, but as an event that created space, time, matter, energy, and the rules governing all of them. The first fraction of a second involved processes so extreme we can barely describe them with our current theories. The next few minutes forged the simplest elements. The next few 100,000 years saw light trapped in a fog. Then the fog cleared, and the universe became the thing we recognize today, transparent, expanding, filled with structure born from quantum noise. But here's the part that almost no one stops to think about. The universe at 1 second old was featureless. At 380,000 years, still featureless, just hydrogen, helium, and light. The stars hadn't formed yet. The galaxies didn't exist. There were no heavy elements, no chemistry, no complexity. The ingredients were there, but nothing had been built. And yet from that blank canvas, given nothing but gravity, time, and the faint ripples left over from inflation, the universe assembled itself into something capable of looking back and asking where it came from. That transformation from a cloud of primordial gas to a structure capable of producing planets, life, and consciousness is the rest of the story. And it all started with rules written in the first moments after the Big Bang. Those rules were encoded in the behavior of particles so small we're still not sure what they're made of. And here's where things get genuinely strange. Because when you zoom in far enough, when you push past the scale of planets and cities and people and cells and molecules and go all the way down to the level of atoms, the universe stops behaving like anything you've ever experienced. The rules change, the logic breaks, and the solid, dependable reality you've spent your entire life trusting turns out to be mostly empty space held together by forces that don't make sense. Take the chair you're sitting in right now. Solid, right? You can feel it. It's supporting your weight. If you knocked on it, you'd hear a thump. It feels real in the most obvious, undeniable way. But zoom in, keep zooming, past the wood grain or the fabric or whatever material it's made of, past the individual fibers, past the molecules, down to the atoms themselves. An atom is about 1/10,000,000th of a meter across. That's 0.1 nanometers, 100,000 times smaller than a human cell. And here's the part that should bother you. An atom is almost entirely empty. At the center of every atom is a nucleus, a tiny cluster of protons and neutrons packed together by the strong nuclear force. The nucleus is incredibly small. If you scaled an atom up to the size of a football stadium, the nucleus would be about the size of a marble sitting at the 50-yard line. Everything else, the entire rest of the stadium, is empty space. Well, not quite empty. It's occupied by electrons, but electrons are so light, so insubstantial, that calling them particles in the traditional sense is already stretching the definition. An electron weighs about 1/2000th the mass of a proton, and they don't orbit the nucleus the way planets orbit a star. That's the picture you probably learnt in school, the little solar system model with electrons zipping around in neat circular paths. It's wrong, totally wrong. Electrons don't have defined paths. They exist in clouds, regions of probability where they might be found if you bothered to look. The technical term is an orbital, and it's not a trajectory, it's a shape. A three-dimensional probability distribution describing where the electron is likely to be at any given moment. So when you're sitting in that chair and you feel the solid surface pressing against you, what's actually happening? The atoms in your body and the atoms in the chair are getting close to each other, close enough that the electron clouds start to overlap. And because electrons are negatively charged and like charges repel, the clouds push back. That repulsion, that electromagnetic force between overlapping electron clouds, is what you interpret as solidity. You're not actually touching the chair in any meaningful sense. You're hovering above it, held up by the mutual repulsion of trillions of tiny negatively charged clouds that refuse to occupy the same space. You have never touched anything in your life, not really. Every surface you've ever felt, every hand you've ever shaken, every hug, every kiss, it's all been electron clouds pushing back against each other across a gap too small to measure. The sensation of touch is a fiction your brain constructs from electromagnetic repulsion. That alone should rearrange how you think about the world, but it gets worse. Because the electron clouds themselves, those regions of probability, don't just sit there waiting to be found. They're not little balls hiding in a shell. The electron, until you measure it, doesn't have a definite position. It's not that we don't know where it is, it's that it doesn't have a where. It exists in a superposition, a term that sounds like physics jargon, but is actually a precise description of something genuinely bizarre. The electron is, in some sense, everywhere in the cloud at once, all possible positions at the same time. The moment you try to measure its location, the superposition collapses. The electron picks a spot, or appears to, and that's where you find it. But before the measurement, it wasn't there. It wasn't anywhere. It was smeared out across the possibilities. This is not a metaphor. This is not a limitation of our instruments. This is how quantum mechanics describes the world, and every test we've ever done confirms it. Superposition is real. Particles exist in multiple states simultaneously until something forces them to choose, and the thing that forces them to choose is measurement, observation, the act of looking. That sounds mystical. It sounds like consciousness has some special role in the fabric of reality, like the universe needs an observer to decide what's real, and that interpretation has caused more confusion and more bad philosophy than almost any other idea in physics. So let's be clear. The word observation in quantum mechanics doesn't mean a conscious being looking at something. It means an interaction, any interaction. When a photon bounces off an electron and gets absorbed by a detector, that's an observation. When an electron collides with another particle and exchanges energy, that's an observation. The universe doesn't need you personally to collapse the wave function. It just needs stuff to interact with other stuff, and stuff is always interacting. But the fact that measurement changes the system is still deeply weird. In classical physics, if you want to measure the position of a baseball, you bounce light off it. The light reflects into your eye or a camera, and you note where the ball is. The ball doesn't care. Its position was what it was before you looked, and the act of looking didn't change anything meaningful. In quantum mechanics, that breaks. Measuring the position of an electron requires interacting with it in a way that disturbs it. And because the electron was in a superposition before you measured it, the act of measurement doesn't just disturb the state, it creates the state. You're not uncovering a pre-existing fact. You're collapsing possibilities into a single outcome. The electron's position wasn't determined until the measurement happened. Before that, the question, "Where is the electron?" didn't have an answer. Not because we lacked information, but because the universe itself hadn't decided yet. Wave-particle duality is another piece of the puzzle that refuses to fit into any intuitive picture. Light, for most of the history of physics, was understood to be a wave. It diffracts around corners. It produces interference patterns when two beams overlap. Young's double-slit experiment in 1801 seemed to settle the question. Light is a wave, case closed. Then in 1905, Einstein showed that light also behaves like a particle. He explained the photoelectric effect, the phenomenon where light knocks electrons out of a metal surface, by treating light as a stream of discrete packets called photons. Each photon carries a specific amount of energy, and if that energy is high enough, it can eject an electron. Wave behavior couldn't explain that. You needed particles. Einstein won the Nobel Prize for it, not for relativity, for explaining light as a particle. So which is it, wave or particle? The answer, annoyingly, is both. Light behaves like a wave in some experiments, and like a particle in others. What determines which behavior you see is the experiment you set up. If you design an experiment to detect wave properties, you'll see waves. If you design an experiment to detect particle properties, you'll see particles. And it's not just light. Electrons do this too. Fire a beam of electrons at a screen with two slits, and you'll get an interference pattern on the far side, the hallmark of wave behavior. Each electron seems to pass through both slits at once, interfering with itself and producing alternating bands of high and low probability on the detector. Close one of the slits and the interference disappears. The electron behaves like a particle that went through the open slit. Place a detector at the slits to see which one the electron passes through, and again, the interference vanishes. The act of measuring which slit the electron used destroys the wave behavior. The electron stops interfering with itself and starts acting like a classical particle following a single path. This isn't a quirk of bad experimental design. It's a fundamental feature of reality at small scales. The electron doesn't have a definite path until you force it to by measuring. Before that, it's in a superposition of going through both slits. And that superposition produces the interference pattern. Measure the path, collapse the superposition, lose the interference. You can't have both. The universe makes you choose. You can know the wave properties or the particle properties, but not both at the same time. This isn't uncertainty in the sense of lacking information. It's a trade-off written into the structure of quantum mechanics itself. The more precisely you measure one property, position for example, the less precisely you can know another property, like momentum. Heisenberg's uncertainty principle. It's not a statement about our tools, it's a statement about nature. The universe has limits on what can be simultaneously known, and those limits aren't technical, they're fundamental. Then there's entanglement, which Einstein hated so much, he spent years trying to prove it couldn't be real. Entanglement happens when two particles interact in such a way that their quantum states become linked. Once entangled, measuring a property of one particle instantly determines the corresponding property of the other, no matter how far apart they are. And when I say instantly, I mean faster than light could travel between them. Measure the spin of one electron, and the spin of its entangled partner, even if it's on the other side of the galaxy, is immediately determined, not because information traveled between them, but because the two particles don't have independent states anymore. They're part of a single quantum system, and measuring one collapses the superposition for both. Einstein called this spooky action at a distance, and he thought it was proof that quantum mechanics was incomplete. There had to be hidden variables, he argued, some deeper layer of reality that we weren't seeing. The particles had to have definite properties all along, and the apparent randomness of quantum mechanics was just ignorance of those hidden details. In 1964, a physicist named John Bell figured out a way to test this. He derived an inequality, a mathematical relationship that any theory based on hidden variables would have to satisfy. Experiments over the following decades tested Bell's inequality, and they all came back with the same answer. The inequality is violated. There are no hidden variables. The universe really is as weird as quantum mechanics says it is. Entanglement is real. Measuring one particle genuinely affects the other, and the connection between them isn't mediated by anything traveling through space. The particles are correlated in a way that classical physics can't explain and can't reproduce. That doesn't mean you can use entanglement to send messages faster than light. You can't. The results of measurements on entangled particles are random. You can't control what result you get, so you can't encode information in the outcomes. What entanglement does give you is a correlation. If you measure a certain property and get a particular result, you instantly know what result the other experimenter will get when they measure the same property. But neither of you can predict what that result will be ahead of time, and neither of you can use your measurement to send a signal. The randomness prevents communication. The universe is weird, but it's not so weird that it lets you break causality. Still, entanglement has practical uses. Quantum cryptography relies on it. If two parties share an entangled pair of particles, they can use measurements on those particles to generate a shared encryption key. Any eavesdropper trying to intercept the key would have to measure the particles, and measurement disturbs the quantum state. The disturbance is detectable. You'd know someone was listening. It's a form of security guaranteed not by the cleverness of an algorithm, but by the laws of physics themselves. Quantum computers, still in their infancy, also rely on entanglement to perform certain calculations exponentially faster than classical computers. The details get complicated, but the basic idea is that a quantum computer can hold information in superposition, processing multiple possibilities at once, and entanglement allows different parts of the computation to stay coordinated. Whether quantum computers will ever be practical for everyday use is still an open question, but the principle works. We've built small ones, they function, the physics is sound. And yet, despite a century of experimental confirmation, despite technologies that rely on quantum mechanics to function, despite the fact that every prediction the theory has made has been correct, we still don't have a satisfying answer to the question of what's actually happening. There are interpretations, lots of them. The Copenhagen interpretation, the oldest and most widely taught, says that the wave function is a complete description of the system, and measurement collapses it into a definite state. Don't ask what the system was doing before measurement. The question doesn't make sense. Many worlds' interpretation says the wave function never collapses. Every possible outcome happens, but in separate branches of reality. When you measure an electron's spin and get up, there's another branch where you measured it and got down. Both outcomes are real. You just can't see the other branch because you're stuck in this one. Pilot wave theory says particles always have definite positions, and they're guided by a wave that obeys the Schrödinger equation. The randomness in quantum mechanics is real randomness, but the particles themselves are always somewhere, doing something. None of these interpretations change the predictions of quantum mechanics. They all give the same experimental results. They differ only in how they tell the story, in what they claim is actually real underneath the math. And because they make the same predictions, there's no experiment that can decide between them. Physics can tell you what will happen. It can't tell you why. Or rather, it can offer several different stories for why, and all of them work equally well at explaining the data. That ambiguity bothers some people. Others think it's fine. The equations work. The technology works. Maybe the why doesn't matter. But here's what does matter. The quantum world, the world of atoms and electrons and photons, is not a smaller version of the world you see around you. It doesn't follow the same rules. Objects at that scale don't have definite positions or velocities until you measure them. They can be in two places at once. They can pass through barriers that classical physics says should be impenetrable, a phenomenon called quantum tunneling that's responsible for nuclear fusion in the sun and the operation of the device you're using to watch this. Particles can affect each other across distances with no physical connection, and the act of observing a system changes it in ways that aren't just technical inconveniences. They're baked into the structure of reality. That last part is worth sitting with for a moment. In the everyday world, you assume things have properties, whether you're looking at them or not. The chair is in the corner. The car is in the driveway. The moon is in the sky. Your looking at them doesn't create those facts. It just reveals them. Quantum mechanics says that assumption breaks at small scales. A particle doesn't have a position until position is measured. It doesn't have a momentum until momentum is measured. And you can't measure both at the same time with arbitrary precision. The particle isn't hiding its properties from you. It doesn't have them, not in the sense that classical objects do. The properties come into existence when the measurement happens. Before that, the system is in a superposition, a blend of all possible outcomes, and the math describes that blend perfectly. The wave function is the most complete description of the system that the universe allows. There's no deeper layer, no hidden reality waiting to be uncovered. This is it. And somehow, out of that mess, out of particles that don't have locations and waves that collapse when you look at them and objects that are mostly empty space held together by electromagnetic repulsion, the universe builds stability. Atoms hold together, molecules form, chemistry happens. The same electron clouds that are smeared out in superposition also create bonds between atoms, sharing or transferring electrons in ways that produce the endless variety of substances you see around you. Water, salt, steel, DNA, all of it emerges from quantum mechanics. The solid world, the tangible, dependable reality of chairs and floors and planets, is a large-scale approximation, a statistical average over trillions of quantum events happening every second. It works because the numbers are huge. When you have 10 to the 23rd atoms in a sample, the quantum randomness averages out. The superpositions collapse so fast and so often that the system looks classical. It looks like it's following definite rules, and for most practical purposes it is. But the quantum behavior is still there, running underneath. Every chemical reaction is a quantum process. Every time your neurons fire, quantum mechanics is involved in how the molecules interact. The colors you see are determined by which wavelengths of light get absorbed or reflected by electron transitions in atoms. The reason the ground doesn't collapse under your weight is quantum. The reason the sun shines is quantum. Fusion in the solar core relies on quantum tunneling to let protons get close enough to stick together despite their electromagnetic repulsion. Without tunneling, stars wouldn't ignite. The universe would be a cold, dark collection of hydrogen clouds, and nothing interesting would ever happen. So yes, the solid objects around you are illusions in the sense that they're not solid in the way you think they are. They're mostly empty space, and the forces holding them together operate on principles that violate every intuition you've ever developed about how the world works. But those forces are real. The electromagnetic repulsion between electron clouds is as real as anything gets. It's just not the kind of realness your brain was built to understand. Your senses evolved to navigate a world of medium-sized objects moving at medium speeds. They didn't evolve to make sense of atoms, and thank goodness for that, because if you had to consciously process the quantum behavior of every particle in your body, you'd never get anything done. The brain's job is to simplify, to take the incomprehensible complexity of quantum interactions and package it into a model you can use. A model where chairs are solid and floors are flat and light is just light, not a superposition of wave and particle behavior that collapses when you look at it. The cost of that simplification is that the model isn't true. Not at the deepest level. It's useful, it's good enough, but it's not the whole story. And now that we've pulled back the curtain, now that we've looked at what's actually happening underneath, you can't unsee it. The world you're sitting in, the device you're holding, the body you're inhabiting, all of it is a shimmering probabilistic dance of quantum fields interacting with each other in ways that don't make intuitive sense. The rules governing those interactions are some of the most precisely tested laws in all of science. We've measured them to 12 decimal places in some cases. They work. They describe reality with a level of accuracy that borders on the eerie. And yet we still can't say, in plain language, what they mean. What's really going on when a particle is in superposition? What collapse actually is? Whether the wave function is a real thing or just a mathematical tool. Physics can predict. It can calculate. It can build technologies that work. But it can't always explain in a way that satisfies the part of your brain that wants the universe to make sense. Quantum mechanics has been the most successful scientific theory in history, and it's also the least intuitive. The two facts are not unrelated. The universe doesn't owe us intuition. It doesn't care whether we understand it. It just is. And the fact that we've managed to describe its behavior at all, to write down equations that capture the quantum weirdness and make testable predictions, is one of the great achievements of human thought. But those equations describe more than particles and forces. They describe space itself. Because the quantum world doesn't just sit inside reality. It's woven into the fabric of reality. The same fabric that bends and stretches under the weight of matter, that curves around stars and ripples outward from colliding black holes. Space isn't a stage where particles perform. It's part of the performance, and the relationship between space, time, and the matter moving through them is the next piece of the puzzle. space and time are the same thing. That sentence should bother you more than it probably does. We spend our entire lives treating space and time as separate. Space is the stuff around you, the distance between your house and the grocery store, the gap between planets. Time is different. Time is what moves forward while you sit still. It's the thing clocks measure, the thing that turns today into yesterday. They feel completely unrelated, and for most of human history, everyone assumed they were. Then, in 1905, a 26-year-old patent clerk in Switzerland published a paper that broke that assumption into pieces. His name was Albert Einstein, and the paper introduced what we now call special relativity. It wasn't the first time someone had suggested that space and time might be connected. Other physicists had been circling similar ideas, but Einstein was the one who took the math seriously and followed it to its logical conclusion. And the conclusion was absurd. Time is not universal. It does not tick at the same rate for everyone. Two observers moving relative to each other will disagree about how much time has passed, not because their clocks are broken, because time itself runs at different rates depending on how you're moving. The whole thing started with light. By the late 1800s, physicists had a problem. Maxwell's equations, the mathematical framework describing electricity and magnetism, predicted that light was an electromagnetic wave traveling at a specific speed, about 300,000 kilometers per second. That number came straight out of the math, but speed relative to what? If you're driving down the highway at 100 kilometers per hour and you throw a ball forward at 20 kilometers per hour, the ball is moving at 120 kilometers per hour relative to someone standing on the side of the road. Speeds add. That's how motion works. So if light is a wave moving through space, and you're moving through space in the same direction, shouldn't the speed of the light wave change depending on how fast you're going? Experiments said no. In 1887, Albert Michelson and Edward Morley set up an experiment to measure the speed of light in different directions as the Earth moved through space. The Earth orbits the Sun at about 30 kilometers per second. If light's speed depended on the motion of the observer, you'd expect to measure different speeds depending on whether you were moving toward the light source or away from it. Michelson and Morley found no difference. Light always traveled at the same speed, no matter which direction they measured. The result was baffling. It didn't make sense. For nearly 20 years, physicists tried to explain it away. Maybe the Earth was dragging some invisible substance along with it. Maybe the measuring instruments were contracting in just the right way to hide the effect. None of the explanations worked. Einstein's insight was to take the experimental results seriously and see what it implied. If the speed of light is always the same for every observer, no matter how they're moving, then something else has to give. And the thing that gives is time. Here's the setup. Imagine you're on a train moving at a constant speed. You're holding a flashlight and you point it at the ceiling. From your perspective, the light travels straight up, bounces off a mirror on the ceiling, and comes straight back down. Simple. You can calculate how long that takes. The distance is twice the height of the train car, and the speed is the speed of light. Divide distance by speed, and you get the time. Now imagine someone standing on the platform outside watching the train go by. From their perspective, you and the flashlight are moving. When you turn on the flashlight, the light still goes up to the ceiling and comes back down, but while it's traveling, the train moves forward, so the light doesn't go straight up and down. It follows a diagonal path, up and forward to the ceiling, then down and forward to your hand. The path is longer. Same speed, longer distance, more time. The person on the platform measures a longer duration for the light to make the trip than you do inside the train. Both of you are right. Time actually passed more slowly for you on the train than it did for the person on the platform. This isn't an illusion. It's not a trick of perception. Time genuinely runs at different rates for observers in relative motion. This effect is called time dilation, and it's been measured thousands of times. Put an atomic clock on an airplane, fly it around the world, and compare it to an identical clock that stayed on the ground. The clock that flew will show less elapsed time. The difference is tiny, a few hundred nanoseconds, but it's there, it's real. GPS satellites have to account for time dilation, or the system wouldn't work. The satellites orbit at about 20,000 kilometers above the Earth, moving at roughly 14,000 kilometers per hour. At that speed and altitude, time runs differently than it does on the ground. The difference is only about 38 microseconds per day, but GPS needs to be accurate to within a few meters. 38 microseconds of error translates to about 11 kilometers of position error. If the satellites didn't correct for relativity, your GPS would tell you you're in the wrong city. The engineers who designed the system weren't guessing. They built relativistic corrections into the software because Einstein's equations said they had to, and it works. Special relativity also predicts length contraction. Objects moving relative to you appear shorter in the direction of motion, not because they're physically squished, but because space itself is measured differently by observers in relative motion. If you could somehow watch a spaceship fly past you at 90% the speed of light, it would look compressed, like someone squeezed it from the front and back. The people inside the spaceship wouldn't notice anything. From their perspective, they're not moving. You're the one flying past them, and from their point of view, you're the one who looks compressed. Both perspectives are correct. There's no absolute reference frame. No universal notion of what's really moving and what's really at rest. Motion is relative, and because motion is relative, measurements of space and time are relative too. This gets even stranger when you think about simultaneity. Two events that happen at the same time for one observer might not happen at the same time for another observer moving relative to the first. Imagine two firecrackers exploding at opposite ends of a train platform. If you're standing exactly in the middle of the platform and the light from both explosions reaches you at the same instant, you conclude the explosions were simultaneous. But someone on a moving train passing through the platform at high speed will see one explosion before the other. Not because the light took longer to reach them, but because their motion through space changes the order in which the events occur in their reference frame. Simultaneity is not absolute. The universe doesn't have a universal now. What counts as now depends on how you're moving. All of this, time dilation, length contraction, relativity of simultaneity, falls out of one assumption. The speed of light is constant for all observers. Einstein didn't pull that assumption out of thin air. Experiments forced it on him. And once you accept it, the math tells you everything else. Space and time are not separate. They're woven together into a single structure called space-time. An event doesn't happen at a place and a time. It happens at a point in space-time. The separation between two events isn't just a distance and a duration. It's a space-time interval, a combination of both, and that interval is what all observers agree on, even if they disagree about the individual components. Special Relativity was published in 1905, and it was radical enough on its own. But it had a limitation. It only worked for observers moving at constant velocities. It didn't include acceleration, and more importantly, it didn't include gravity. Einstein spent the next 10 years trying to figure out how to extend relativity to cover accelerated motion and gravitational fields. The result, published in 1915, was general relativity, and it completely rewrote our understanding of gravity. Newton's theory of gravity, which had worked perfectly for more than 2 centuries, treated gravity as a force. Massive objects attract each other across empty space. The Earth pulls on the Moon. The Sun pulls on the Earth. Gravity reaches out, invisibly, instantaneously, and tugs. Newton himself admitted he had no idea how it worked. He could calculate the effects with extraordinary precision, but the mechanism was a mystery. Einstein solved the mystery by getting rid of the force. In general relativity, gravity isn't a force at all. It's the curvature of space-time. Here's the idea. Massive objects don't pull on each other. They warp the fabric of space-time around them. A planet doesn't orbit a star because the star is pulling it. It orbits because the star's mass curves space-time, and the planet is following the straightest possible path through that curved space. Imagine a bowling ball sitting on a trampoline. The trampoline sags under the weight of the ball. Now roll a marble across the trampoline. The marble doesn't travel in a straight line. It curves toward the bowling ball, not because the bowling ball is pulling it, but because the surface it's rolling on is curved. That's gravity. Mass tells space-time how to curve. Curved space-time tells objects how to move. The analogy breaks down if you push it too far. The trampoline is two-dimensional, and it's sagging in a third spatial dimension because of Earth's gravity. Space-time is four-dimensional, and it's not curving into anything external. The curvature is intrinsic, but the basic picture holds. Gravity is geometry. The presence of mass and energy changes the shape of space-time, and objects moving through that curved space-time follow paths that look, to us, like they're being pulled by a force. But there's no force, there's just curvature. This prediction is testable, and it was tested almost immediately. One of the first major confirmations came in 1919. Einstein's equations predicted that light, even though it has no mass, should be affected by gravity because light travels through space-time, and space-time is curved. If you shine a beam of light past a massive object, the light should bend. Newton's theory also predicted a tiny amount of bending, but general relativity predicted more. The difference was measurable. During a total solar eclipse in May of 1919, a team led by Arthur Eddington traveled to the island of Principe off the west coast of Africa to photograph stars near the sun. The eclipse made the stars visible during the day, and Eddington measured their positions. He compared those positions to where the stars appeared at night when the sun wasn't in the way. The stars near the sun were shifted, exactly as Einstein predicted. Light bends around massive objects. Space-time is curved. The announcement made Einstein an international celebrity overnight. Since then, we've measured gravitational lensing, the bending of light by massive objects, thousands of times. Galaxies and galaxy clusters warp the light from more distant objects behind them, creating arcs, rings, and multiple images of the same background galaxy. The Hubble Space Telescope has captured stunning examples. One cluster, called Abell 2218, acts like a giant lens, distorting the light from galaxies billions of light-years farther away. The distortions match general relativity's predictions. Every measurement we've made confirms that gravity is the curvature of space-time. But general relativity also predicts something much more extreme. If you compress enough mass into a small enough volume, the curvature becomes so severe that not even light can escape. The object collapses into a black hole. The defining feature of a black hole is the event horizon, the boundary beyond which nothing, not matter, not light, not information, can ever return. Cross the event horizon, and your future is no longer in the rest of the universe. It's entirely inside the black hole. You fall toward the center, toward a point called the singularity, where the curvature becomes infinite and the equations break down. General relativity predicts the singularity, but it can't describe what happens there. The theory stops working. That's a sign that something deeper is going on, probably something involving quantum mechanics. but nobody has figured out how to combine quantum mechanics and general relativity into a single consistent theory. Not yet. Black holes were a mathematical curiosity for decades. Physicists weren't sure they actually existed. The equations allowed them, but that didn't mean nature built them. Then, in the 1960s and 70s, astronomers started finding objects that fit the description. Compact, massive, invisible, surrounded by swirling disks of superheated gas. The gas emits X-rays as it spirals inward, and those X-rays are detectable from Earth. One of the first candidates was Cygnus X1, an X-ray source in the constellation Cygnus. Observations showed a visible star orbiting an invisible companion roughly 15 times the mass of the Sun. No known object other than a black hole could be that massive and that compact. Cygnus X1 is now considered one of the strongest pieces of evidence for stellar mass black holes. But the most dramatic evidence came much more recently. In 2019, the Event Horizon Telescope collaboration released the first image of a black hole's shadow, not the black hole itself. You can't photograph something that doesn't emit light, but you can photograph the glowing gas around it. The target was the supermassive black hole at the center of the galaxy Messier 87, about 55 million light-years away. The black hole weighs roughly 6.5 billion times the mass of the Sun, and the shadow it casts is enormous. The image showed a bright ring of light surrounding a dark circle. The dark circle is the shadow, the region where light is either falling into the black hole or bent so severely by space-time curvature that it never reaches us. The ring is the photon sphere, where light orbits the black hole before escaping or falling in. The shape, the size, the brightness distribution, all of it matched the predictions of general relativity. The equations Einstein wrote down in 1915 were describing an object 55 million light-years away with a mass 6 billion times that of the Sun. And the match was nearly perfect. In 2022, the Event Horizon Telescope released a second image, this time of Sagittarius A star, the supermassive black hole at the center of our own Milky Way galaxy. It weighs about 4 million solar masses, much smaller than the one in Messier 87, but it's much closer, only about 27,000 light-years away. The image showed the same structure, a dark shadow surrounded by a glowing ring. Two different black holes, two different galaxies, same physics. General relativity works. Black holes are the most extreme examples of space-time curvature we know of, but they're not the only evidence that space-time can be dynamic. In 2015, the Laser Interferometer Gravitational Wave Observatory, LIGO, detected gravitational waves for the first time. Gravitational waves are ripples in space-time itself, produced when massive objects accelerate, colliding black holes, merging neutron stars. Anything that involves large masses changing speed or direction sends ripples outward at the speed of light. Those ripples stretch and squeeze space as they pass. The effect is tiny. When the first gravitational wave signal reached Earth on September 14, 2015, it changed the distance between LIGO's mirrors by less than 1,000th the width of a proton. LIGO is sensitive enough to measure that. The signal came from two black holes, each about 30 times the mass of the Sun, that had been spiraling toward each other for millions of years. In the final fraction of a second before they merged, they were orbiting each other hundreds of times per second, moving at a significant fraction of the speed of light. The collision released more energy in gravitational waves than all the stars in the observable universe were emitting in light at that same moment. And all of that energy was carried away as ripples in space-time. The waves traveled outward for 1.3 billion years, spreading across the cosmos until they reached Earth and jiggled LIGO's mirrors by an amount smaller than an atomic nucleus. Since that first detection, LIGO and its European counterpart Virgo have detected dozens more gravitational wave events. Most are black hole mergers, a few are neutron star collisions. One neutron star merger, detected in August 2017, was observed simultaneously in gravitational waves and electromagnetic radiation. Telescopes around the world saw the explosion. The afterglow was visible for weeks. The event, called a kilonova, is thought to be one of the primary sources of heavy elements like gold and platinum in the universe. The gravitational wave signal told astronomers exactly where to point their telescopes. For the first time, we could watch a cosmic event unfold in two completely different ways. Light and space-time ripples, both carried information. Together, they told the full story. Gravitational waves are now a tool. Astronomers use them to study objects that don't emit light. Black holes, for instance, are invisible. You can't see them directly. But when two black holes merge, they scream in gravitational waves. LIGO hears that scream, and from the signal's shape, frequency, and duration, physicists can calculate the masses of the black holes, how fast they were spinning, how far away the collision happened, and how much energy was released. It's a new way of observing the universe. Not with light, but with the vibrations of space-time itself. The existence of gravitational waves was predicted by Einstein in 1916, 1 year after he published General Relativity. The equations said that accelerating masses should produce ripples, but Einstein himself thought the effect would be too weak to ever detect. He was almost right. It took a century of technological development, billion-dollar instruments, and thousands of scientists to prove he was wrong. The waves are real. Space-time is not a static backdrop. It bends, it ripples, it responds to the presence of mass and energy. And that responsiveness is what we call gravity. All of this, time dilation, curved space-time, black holes, gravitational waves, comes from taking seriously the idea that space and time are not separate. They're aspects of a single structure. You can't have space without time. You can't have time without space. An event is a point in space-time, and the distance between events depends on both spatial separation and temporal separation. Moving through space means moving through time. Sitting still in space still means moving through time. There's no such thing as being motionless in space-time. You're always moving forward through time at the very least. The faster you move through space, the slower you move through time, in such a way that your total motion through space-time stays constant. This is why nothing can travel faster than light. Light moves through space at the maximum possible speed, which means it doesn't move through time at all. From a photon's perspective, if it had one, the journey from a star to your eye is instantaneous. It's emitted and absorbed in the same moment. The fact that you measure millions or billions of years passing is because you're moving through time. The photon isn't. The interconnection of space and time is not a detail. It's the foundation. Once you accept that the speed of light is constant, everything else follows. Time runs at different rates. Lengths contract. Simultaneity is relative, and massive objects warp the structure that everything moves through. The universe is not a stage with actors on it. The stage is part of the performance. It bends, it stretches, it ripples, it has a shape, and that shape is determined by what's in it. Empty space is flat. Add mass, and it curves. Add enough mass in a small enough region, and it curves so much that it closes off, creating a black hole. Add mass everywhere, distributed more or less evenly, and you get the large-scale curvature of the universe itself. That large-scale curvature has been measured. The universe, on average, is flat. Not flat in the sense of being two-dimensional. Flat in the sense that parallel lines stay parallel, and the angles of a triangle add up to 180 degrees. That's what flat means in the geometry of space-time. A curved universe would behave differently. Parallel lines might converge or diverge. Triangles might have more or less than 180 degrees. Current measurements say the universe is flat to within about 0.5%. That flatness is one of the reasons physicists think cosmic inflation happened. Inflation stretches space so much that any initial curvature gets smoothed out, the same way inflating a balloon makes its surface look flatter the bigger it gets. A universe that underwent inflation should be flat. Ours is. Not proof, but consistent. General relativity also predicts that the universe as a whole should be either expanding or contracting. It can't be static. Einstein initially didn't like that prediction. He thought the universe was eternal and unchanging, so he added a term to his equations called the cosmological constant to hold everything still. Then, in 1929, Edwin Hubble showed that distant galaxies were moving away from us. The universe is expanding. Einstein reportedly called the cosmological constant his biggest blunder. Though, interestingly, the cosmological constant has come back in a different form. Modern cosmology uses it to describe dark energy, the mysterious force causing the expansion to accelerate. Whether that's what Einstein had in mind doesn't matter. The equations allowed it, and the universe seems to be using it. The expansion of space itself is another consequence of general relativity. Space isn't a container, it's a dynamic thing. It can grow. When we say the universe is expanding, we don't mean galaxies are flying away from each other through space. We mean the space between them is growing. The galaxies are mostly stationary. The fabric they're embedded in is stretching. An ant walking on a rubber band isn't moving if someone stretches the rubber band. The ant's position on the band hasn't changed, but the distance between the ant and a spot further down the band increases. That's what's happening to galaxies. The expansion is happening everywhere, all the time. It's not expanding into anything. There's no outside. Space itself is getting bigger. And this brings us to the edge of what general relativity can describe. The theory works beautifully at every scale we've tested. Solar system orbits, gravitational lensing, black hole mergers, cosmological expansion, all of it fits. But general relativity is a classical theory. It doesn't include quantum mechanics. And at the smallest scales, inside black holes, or in the first moments after the Big Bang, both gravity and quantum effects are important. We need a theory that combines both. Physicists have been trying to build one for decades. String theory, loop quantum gravity, and other approaches have made progress, but none have succeeded completely. The math is hard. The experiments are nearly impossible. We can't build a particle collider powerful enough to probe the energy scales where quantum gravity matters. What we can do is observe, look at black holes, measure gravitational waves, study the cosmic microwave background, test general relativity in every regime we can reach. And so far, every test has confirmed Einstein's equations. A century after they were written, they still describe the universe with stunning accuracy. Space-time is real. It bends, it ripples, it defines the paths that matter and light follow. Gravity is not a force reaching across the void. It's the shape of the void itself. The universe we inhabit is not the static, absolute space Newton imagined. It's a shifting, flexible structure that responds to what's in it. And what's in it, the stars and planets and gas and dust, all of it came from processes that took billions of years to unfold. Processes that turned primordial hydrogen into the complexity we see around us today. Processes that built the elements, the chemistry, and eventually the conditions where something like life could begin to ask what all of this means. The universe, after shaping space and bending time, had one more trick to perform. It had to build something interesting. And for the first few 100 million years after the Big Bang, it wasn't clear that would happen. You had hydrogen, you had helium, you had trace amounts of lithium and beryllium, leftovers from those first 3 minutes of nuclear synthesis. And that was it. The entire periodic table of elements, everything from carbon to uranium, all the complexity that makes chemistry possible, none of it existed yet. The universe was a featureless fog of the simplest atoms drifting through expanding space with nothing to do and no way to do it. But gravity doesn't care about simplicity. Gravity just pulls. And in the faint density fluctuations left over from cosmic inflation, fluctuations measured at 1 part in 100,000, gravity had something to work with. Regions that were slightly denser than average pulled in more matter. As they pulled in more matter, they became denser still. The denser they became, the harder they pulled. It's a runaway process. A slight advantage compounds into a massive one given enough time. And the early universe had time, millions of years, tens of millions. Whole epochs where nothing visible was happening. But underneath, in the slow, invisible churn of gravitational collapse, the first structures were beginning to form. The first stars ignited somewhere between 100 million and 250 million years after the Big Bang. Nobody has directly observed one. They're too far away, too faint, and they didn't last long. But the models are clear. These stars, called population 3 stars, were monsters. Without heavier elements to cool the collapsing gas clouds, the clouds had to be enormous to collapse at all. The first stars likely weighed anywhere from a few dozen to a few hundred times the mass of our Sun. Some models suggest individual stars could have reached 1,000 solar masses, though that's at the extreme end. Either way, they were huge, hot, and incredibly short-lived. A star that size burns through its fuel in a few million years. For comparison, our Sun has been burning steadily for about 4.5 billion years and has another 5 billion to go. Population 3 stars didn't get that luxury. They ignited, burned blue-white with surface temperatures exceeding 50,000 degrees, and then exploded. And when they exploded, they seeded the surrounding space with the first heavy elements the universe had ever seen: carbon, oxygen, nitrogen, silicon, iron, all of it forged in the cores of those dying stars and scattered outward in the supernova blast. The explosions were so energetic that they created elements even heavier than iron, things like gold and platinum and uranium, which require conditions so extreme that even the interior of a normal star isn't enough. You need a supernova, or, as we now know, a neutron-star collision. Either way, the point is the same. The elements that make up planets, that make up your body, that make up every piece of technology you've ever used, all of it had to be built inside stars. The universe started with hydrogen and helium. Everything else is stellar ash. The first galaxies began to take shape within the first few 100 million years. They weren't like the galaxies we see today. They were smaller, messier, more chaotic. Dwarf galaxies, irregular clumps of stars held together by gravity and surrounded by halos of dark matter. Over time, those dwarf galaxies merged. Gravity pulled them together, and the collisions triggered bursts of star formation. Gas clouds slammed into each other, compressed, heated, and ignited into new generations of stars. Each generation lived, died, and enriched the surrounding gas with heavier elements. The universe was slowly building a chemical inventory. By the time the universe was 1 billion years old, galaxies were everywhere. Large spiral galaxies like the Milky Way hadn't fully formed yet, but the building blocks were in place. Stars were being born by the billions, and with each generation, the metallicity, the fraction of elements heavier than helium, was increasing. The first stars had zero metallicity, pure hydrogen and helium. The second generation, population 2 stars, had a tiny bit of carbon and oxygen mixed in, maybe 1 part in 10,000. Our Sun, a population 1 star, has a metallicity of about 2%. That doesn't sound like much, but it's enough. 2% heavy elements is enough to make rocky planets. It's enough to make water. It's enough to make life. Stellar nuclear synthesis, the process by which stars build heavier elements, follows a predictable sequence. A star like our Sun spends most of its life fusing hydrogen into helium in its core. The process releases energy, and that energy creates an outward pressure that balances the inward pull of gravity. As long as the hydrogen lasts, the star stays stable. When the hydrogen in the core runs out, the core contracts and heats up. Eventually it gets hot enough to start fusing helium into carbon. The outer layers of the star expand, and the star becomes a red giant. Our Sun will do this in about 5 billion years. It will swell up and swallow the inner planets, possibly including Earth. Then it will shed its outer layers into space, creating a planetary nebula, and the core will collapse into a white dwarf, a dense, hot ember about the size of Earth, slowly cooling over billions of years. More massive stars go further. They fuse carbon into oxygen, oxygen into neon, neon into magnesium, and so on up the periodic table. Each stage produces heavier elements and releases less energy. The star is running out of fuel. Eventually, if the star is massive enough, it builds an iron core. Iron is the end of the line. Fusing iron doesn't release energy, it absorbs energy. Once the core is iron, there's nothing left to hold the star up. Gravity wins. The core collapses in less than a second, and the outer layers come crashing down. When they hit the rigid core, they bounce. The rebound drives a shockwave outward through the star, and the star explodes. A core collapse supernova. For a few weeks, the exploding star can outshine an entire galaxy, and in that explosion, almost every element heavier than iron is created and hurled into space. The remnants of the explosion, the gas and dust enriched with heavy elements, eventually become part of new clouds. Those clouds collapse under gravity, new stars form, the cycle continues. This is how the universe builds complexity, slowly, violently, one generation at a time. The hydrogen you're made of is primordial, left over from the Big Bang. The carbon in your bones, the oxygen in your lungs, the iron in your blood, all of it was cooked inside a star that exploded billions of years ago, long before the Sun or the Earth existed. You are, quite literally, made of stardust. That's not poetry, that's astrophysics. Our solar system formed about 4.5 billion years ago from the collapse of a molecular cloud, a cold, dense region of gas and dust in the spiral arm of a young Milky Way galaxy. Something disturbed the cloud, possibly the shock wave from a nearby supernova. The cloud began to collapse. As it collapsed, it started to spin. Conservation of angular momentum. The same reason a figure skater spins faster when they pull their arms in. The collapsing cloud flattened into a disk, with most of the mass falling into the center. That central concentration became the Sun. The leftover material in the disk, about 1% of the total mass, clumped together to form the planets. Close to the Sun, where temperatures were high, only materials with high melting points could condense. Metals and silicates, rocky planets, Mercury, Venus, Earth, Mars. Farther out, beyond the frost line, where temperatures dropped below the freezing point of water, ice could form. The planets out there, Jupiter, Saturn, Uranus, Neptune, grew much larger because they could incorporate not just rock and metal, but also vast amounts of ice and gas. Jupiter alone contains more mass than all the other planets combined. It's a failed star, in a sense. If it had been about 80 times more massive, the core would have ignited fusion and it would have become a second sun. It didn't. It stayed a planet. A very large planet with a moon system that looks like a miniature solar system, but a planet nonetheless. Earth formed through a process called accretion. Small particles of dust stuck together through static electricity and van der Waals forces. Dust became pebbles, pebbles became rocks, rocks became boulders, boulders became planetesimals, objects a few kilometers across. Planetesimals collided and merged, growing into protoplanets. The whole process took a few tens of millions of years, which sounds like a long time, but is geologically instantaneous. By about 4.5 billion years ago, Earth had reached roughly its current size. It was molten. The surface was an ocean of magma, constantly bombarded by leftover debris from the planet-forming process. Then, roughly 50 million years after Earth formed, a Mars-sized protoplanet called Theia slammed into it. The collision was catastrophic. Both objects were partially vaporized. The debris from the impact formed a ring around Earth, and that ring eventually coalesced into the Moon. The impact also tilted Earth's axis, giving us our seasons, and may have delivered additional volatile compounds like water. We're still not entirely sure where Earth's water came from. Some of it probably came from asteroids and comets that impacted the surface after it cooled. Some might have been present in the material that formed the planet in the first place. The discovery of exoplanets, planets orbiting stars other than the Sun, has completely rewritten our understanding of planetary systems. Before 1995, the only planets we knew about were the 8 in our solar system. 9, if you count Pluto, which was still considered a planet at the time. Astronomers assumed other stars had planets, but no one had detected any. Then in 1995, Michael Mayer and Didier Queloz announced the discovery of 51 Pegasi b, a Jupiter-sized planet orbiting a Sun-like star about 50 light-years away. The planet was strange. It orbited its star in just over 4 days, far closer than Mercury orbits our Sun. It was a hot Jupiter, a class of planet that shouldn't exist according to the models. Gas giants were supposed to form far from their stars, where it's cold enough for ice to exist. 51 Pegasi b was orbiting so close that its surface temperature was over 1,000 degrees. The discovery opened the floodgates. Over the next few decades, astronomers found thousands of exoplanets. As of late 2024, the confirmed count is over 5,000, with thousands more candidates waiting for confirmation. The methods for detecting them have become increasingly sophisticated. The radial velocity method, which Mayer and Queloz used, watches for the wobble in a star's motion caused by an orbiting planet. The star and the planet both orbit their common center of mass, and that causes the star to shift slightly toward and away from us. The shift shows up as a Doppler shift in the star's spectrum. The transit method watches for the dimming of a star's light as a planet passes in front of it. If the planet's orbit is aligned just right, it will block a tiny fraction of the star's light once per orbit. The Kepler Space Telescope, which operated from 2009 to 2018, used the transit method to find over 2,700 confirmed planets. Its successor, the Transiting Exoplanet Survey Satellite, TESS, has found thousands more. What we've learned from exoplanets is that planetary systems are common, extremely common. Current estimates suggest there are more planets in the Milky Way than there are stars. Most stars have at least one planet. Many have multiple. The diversity is staggering. We've found planets smaller than Mercury and planets more massive than Jupiter. Planets that orbit their stars in hours and planets that take hundreds of years. Planets made of rock, of ice, of gas, possibly even of molten lava or solid diamond. Systems with planets in tight orbits, systems with planets spread far apart, systems where planets orbit binary stars. Every new discovery seems to violate some assumption we'd made about how planetary systems should work. The universe, it turns out, is more creative than we gave it credit for. The search for life beyond Earth has naturally focused on planets that might resemble ours. Earth-sized rocky planets orbiting in the habitable zone, the region around a star where temperatures are right for liquid water to exist on the surface. Water is the key. Every form of life we know of requires water. It's a solvent, a transport medium, a participant in biochemical reactions. Life without water might be possible in some exotic chemistry we haven't thought of, but life with water is the only kind we know how to look for. So we look for planets where water could be liquid, not too hot, not too cold, and we've found dozens of candidates. Planets like Proxima Centauri b, orbiting the nearest star to our Sun. Planets in the TRAPPIST-1 system, where 7 Earth-sized worlds orbit a dim red dwarf star, and at least 3 of them are in the habitable zone. Planets like Kepler 442b, a super-Earth about twice our size, orbiting a star slightly cooler than the Sun. All of them are too far away to visit. The nearest is over 4 light-years away. Even traveling at the speed of the fastest spacecraft we've ever built, it would take tens of thousands of years to get there. But we can study them from here. We can analyze the light filtering through their atmospheres and look for chemical signatures of life. Oxygen, methane, compounds that don't belong in a sterile atmosphere. The James Webb Space Telescope has already started doing this. So far, no smoking gun, but the search has just begun. Back on Earth, life began at some point after the planet cooled and the oceans formed. We don't know exactly when. The oldest confirmed fossils are about 3.5 billion years old, microbial mats preserved in ancient sedimentary rocks in Australia and South Africa. There's indirect evidence, chemical signatures in even older rocks, that suggests life might have been around as early as 4 billion years ago, only 500 million years after Earth formed. If that's true, life arose quickly, geologically speaking, almost immediately. We don't know how it happened. The origin of life, abiogenesis, is one of the biggest open questions in science. We know the ingredients. Organic molecules, compounds based on carbon, were present on early Earth. We've found amino acids, the building blocks of proteins, in meteorites. We've created them in lab experiments designed to mimic early Earth conditions. The Miller-Urey experiment in 1953 showed that you could generate amino acids by running electrical sparks through a mixture of water, methane, ammonia, and hydrogen, a combination thought to resemble the early atmosphere. Later experiments have used different gas mixtures and different energy sources, lightning, ultraviolet light, volcanic heat, and they've produced a wide variety of organic molecules. The chemistry is there, but getting from organic molecules to life is a massive jump. A living cell, even the simplest bacterium, is breathtakingly complex. It has a membrane that separates inside from outside. It has metabolism, a set of chemical reactions that extract energy from the environment and use it to build and repair structures. It has information storage, DNA or RNA, that carries instructions for making proteins. And it has a way to replicate, to make copies of itself. All of these features had to come together somehow. The order in which they appeared, the intermediate steps, the selection pressures that drove the process, none of it is certain. There are hypotheses, lots of them. The RNA world hypothesis suggests that early life was based on RNA, which can both store information like DNA and catalyze reactions like proteins. The metabolism first hypothesis suggests that self-sustaining chemical cycles arose before anything resembling a cell. The lipid world hypothesis focuses on how membranes might have formed spontaneously from fatty molecules in water. Each idea has evidence supporting it. None of them is complete. What we can say is that once life got started, it changed the planet. Early life was anaerobic. It didn't use oxygen because there wasn't any free oxygen in the atmosphere. Then, about 2.5 billion years ago, cyanobacteria, photosynthetic microbes, began producing oxygen as a waste product. Oxygen is reactive. It binds with other elements. Initially, all the oxygen produced by cyanobacteria was absorbed by dissolved iron in the oceans, forming iron oxide, rust, which settled to the ocean floor. Massive deposits of banded iron formations, layers of rust interspersed with other sediments, are the geological record of this process. Eventually, the oceans were saturated. There was no more iron left to react with. The oxygen began accumulating in the atmosphere. This was an environmental catastrophe. Oxygen was toxic to most of the life that existed at the time. Many species went extinct, but some organisms adapted. They evolved ways to use oxygen in their metabolism, and it turned out oxygen was an incredibly efficient energy source. Aerobic respiration, the process most complex life uses today, extracts far more energy from food than anaerobic processes. The rise of oxygen in the atmosphere, an event called the Great Oxidation Event, paved the way for complex life. Complex life, meaning multicellular organisms, didn't appear until much later. For over 2 billion years after the Great Oxidation Event, life stayed simple. Bacteria, archaea. Eventually, eukaryotes, cells with a nucleus, appeared. Eukaryotic cells are thought to have originated through a process called endosymbiosis, where one cell engulfed another and the engulfed cell became a permanent resident. Mitochondria, the energy-producing structures in eukaryotic cells, were once free-living bacteria. Chloroplasts, the structures that perform photosynthesis in plant cells, were once cyanobacteria. The evidence for this is overwhelming. Mitochondria and chloroplasts have their own DNA, separate from the cell's nucleus. Their DNA is circular, like bacterial DNA. They replicate independently of the cell. They even have double membranes, consistent with being engulfed by another cell. Eukaryotes are chimeras, composite organisms built from multiple lineages that merged. Multicellular life appeared around 600 million years ago. Before that, eukaryotes were single-celled. Then something changed. Cells began sticking together after dividing. They began specializing. Some cells became good at movement, others at sensing the environment, others at reproduction, division of labor, cooperation. The advantages were enormous. A multicellular organism can grow larger, explore more of the environment, resist predators, and adapt to changing conditions in ways a single cell can't. Once multicellularity evolved, it exploded. Within a few tens of millions of years, the Cambrian explosion, the fossil record, shows a sudden appearance of almost every major animal body plan we see today. Arthropods, mollusks, chordates, echinoderms, all of them appearing in a geological blink. From there, evolution continued. Life colonized the land, plants first, then arthropods, then vertebrates. Forests grew. Ecosystems became more complex. Extinction events wiped out large fractions of life multiple times. The most severe, the Permian-Triassic extinction about 250 million years ago, killed over 90% of marine species and 70% of terrestrial vertebrates. Life recovered. It always has. New species filled the empty niches. Dinosaurs ruled the land for over 150 million years. Then, 66 million years ago, an asteroid about 10 kilometers across slammed into what is now the Yucatan Peninsula in Mexico. The impact triggered massive wildfires, threw enough dust into the atmosphere to block out the sun for years, and caused a global collapse of ecosystems. The dinosaurs, except for the lineage that became birds, went extinct. Mammals, which had been small and mostly nocturnal, suddenly had room to expand. Within 10 million years, they had diversified into most of the major groups we see today. Primates appeared. Eventually, a lineage of primates in Africa developed larger brains, began walking upright, started using tools. Homo sapiens, our species, emerged roughly 300,000 years ago. For most of that time, we lived as hunter-gatherers in small groups. Then, about 10,000 years ago, we invented agriculture. Civilizations followed: writing, mathematics, science. And now, 13.8 billion years after the universe began, a particular arrangement of atoms on a particular planet is looking back at the whole story and trying to figure out how it happened. That journey, from hydrogen clouds to conscious beings, was not guided. There was no plan, no designer, just the laws of physics, the initial conditions set in the first fraction of a second after the Big Bang, and an enormous amount of time. Gravity pulled matter together, stars ignited, heavier elements were forged and scattered, planets formed, chemistry happened. Somewhere along the way, chemistry crossed a threshold and became biology, replicating molecules, cells, organisms, ecosystems, brains. The process was messy, random, and utterly dependent on the specific conditions Earth provided. Change any one of 100 variables and life might never have started. Or it might have started and gone extinct in the first billion years. Or it might have stayed microbial forever. We don't know how many other planets in the universe have followed a similar path. We don't know if the steps that led to us are common or extraordinarily rare. The sample size is 1. What we do know is that the atoms in your body, the ones participating in the chemical reactions that keep you alive, have been on a journey. They were forged in the cores of massive stars billions of years ago. Those stars exploded. The atoms drifted through space, mixed with gas and dust, collapsed into a new cloud, formed a new star and a set of planets. On one of those planets, under conditions we still don't fully understand, those atoms assembled into molecules that could replicate. Those molecules got better at replicating. They formed cells. Those cells got more complex. Eventually, multicellular organisms appeared. One lineage developed nervous systems. Nervous systems got more elaborate. Brains grew larger. And now, here you are, a collection of atoms arranged in such a way that it can think about atoms. The universe has spent 13.8 billion years getting to this point, building structure, building complexity, building through no intention but through the relentless grinding of physical law, a system capable of understanding itself. And that system, your brain, is where the story takes its strangest turn. Because the brain doesn't just process the universe, it constructs it. The colors you see, the sounds you hear, the sense of space and time and self, all of it is a model, a simulation built by neurons firing in patterns determined by signals from your senses. The universe you experience is not the universe itself, it's a representation. And the accuracy of that representation, the degree to which it reflects external reality, is a question worth asking. You are, as we've just established, made of atoms that have been on a 13.8 billion year journey. Hydrogen from the Big Bang, carbon from a dying star, oxygen from a supernova, all of it arranged into cells, tissues, organs, and eventually a brain. A 3-pound lump of tissue sitting in your skull, consuming about 20% of your body's energy, despite making up only 2% of your mass. And that lump is doing something extraordinary right now. It's building a world, not the world, A world, your world, the one you experience. The colors you see, the sounds you hear, the textures you feel, none of them exist in the way you think they do. They're constructions, models built by your brain from incomplete, ambiguous data flooding in through your senses. The universe outside your head is a sea of electromagnetic radiation, air pressure waves, and molecular collisions. The universe inside your head, the one you actually experience, is a simulation, and the gap between those two things is where reality gets complicated. Start with vision, because that's the sense most people trust the most. You open your eyes and you see the world. Simple, direct, except it's not. What's actually happening is that photons, particles of light, are bouncing off objects, and some of them happen to hit your retina. The retina is a thin layer of tissue at the back of your eye, packed with about 130 million photoreceptor cells, rods and cones. Rods handle low light and don't distinguish color. Cones come in 3 types, each sensitive to different wavelengths. Short wavelengths we call blue, medium wavelengths we call green, long wavelengths we call red. When a photon hits a photoreceptor, it triggers a chemical reaction that converts light into an electrical signal. That signal travels along the optic nerve to the brain. But here's the thing, the photoreceptors don't cover the retina evenly. The center of your vision, the fovea, is packed with cones, high resolution, sharp detail. That's why you can read text or recognize faces when you're looking directly at them. But the periphery is mostly rods, lower resolution, good for detecting motion, terrible for detail. And there's a spot in each eye where the optic nerve exits the retina, and that spot has no photoreceptors at all. It's called the blind spot. You have a hole in your vision, 2 holes, actually, 1 in each eye. You don't see them because your brain fills them in. It looks at the surrounding area and guesses what should be there. Most of the time, it guesses correctly, but it's not showing you what's actually there. It's showing you what it thinks should be there, based on context. Your brain is lying to you, and it's so good at it that you never notice. The image that hits your retina is also upside down. The lens in your eye inverts the light as it passes through. Your brain flips it back. When you see a tree, the light from the top of the tree is hitting the bottom of your retina. Your brain knows this and corrects for it automatically. You've been walking around your entire life looking at an upside-down world that your brain has helpfully right-sided for you without asking permission. Oh, and the image is also 2-dimensional. Your retina is flat. The 3-dimensional depth you perceive is a calculation. Your brain uses cues, stereoscopic vision, the slight difference in the images from your 2 eyes, motion parallax, the way objects at different distances move at different speeds when you move your head, perspective, the way parallel lines appear to converge in the distance, occlusion, the way objects in front block objects in back, shadows, texture gradients. It takes all of those cues, runs them through a set of algorithms refined over millions of years of evolution, and produces a sense of depth. That depth is not given to you, it's computed. Color is even stranger. The wavelength of light is a physical property. A photon with a wavelength of about 470 nanometers will hit your retina and trigger a response in your short wavelength cones. That's a fact about the photon. But the blueness you experience, the qual, the subjective sensation, that's entirely in your head. There's no blue in the photon. The photon doesn't have a color, it has a wavelength. Your brain takes that wavelength, processes it, and produces the experience of blue. We all agree to call it blue because we've been trained to use the same word for that experience. But there's no way to know if the blue you see looks the same as the blue I see. We could be having completely different subjective experiences, And we'd never know because we have no way to compare them directly. You can't step into my head and see what blue looks like to me. All we can do is point at the same objects and agree on the label. This gets weirder when you realize that color categories are partly cultural. The wavelength spectrum is continuous. There's no hard boundary where blue stops and green starts. Different languages divide the spectrum differently. Some languages have one word for blue and green. Others have separate words for light blue and dark blue that are as distinct as blue and green are in English. Russian speakers, for instance, distinguish between goluboy, light blue, and siny, dark blue, and they're faster at detecting differences between shades that cross that boundary. The language you speak shapes how you perceive color, not the wavelengths your eyes detect. Those are the same for everyone with normal vision, but the way your brain categorizes and processes those wavelengths is influenced by the linguistic categories you've learned. Your perception is being shaped by culture. Now take sound. Sound is air pressure waves. An object vibrates, pushes air molecules. Those molecules bump into other molecules, and a wave of pressure variations propagates outward. When that wave hits your eardrum, a thin membrane stretched across your ear canal, the eardrum vibrates. The vibrations are transmitted through 3 tiny bones, the smallest bones in your body, to the cochlea. The cochlea is a spiral-shaped structure filled with fluid. Inside the cochlea is the organ of Corti, which contains about 16,000 hair cells. The hair cells have tiny bristles that bend when the fluid moves. Different hair cells respond to different frequencies. High-frequency sounds cause hair cells near the base of the cochlea to fire. Low-frequency sounds cause hair cells near the tip to fire. The firing pattern gets converted into electrical signals and sent to the brain. What you hear is not the air pressure wave. You hear your brain's interpretation of the pattern of hair cell activations. Pitch is a construct. Loudness is a construct. The quality of a sound, what makes a piano sound different from a violin, even when they're playing the same note, that's timbre, and it's based on the mix of overtones present in the sound wave. Your brain analyzes the frequency content and produces a sensation. But the sensation is not the sound wave. The sound wave is a physical vibration. The experience of hearing is entirely in your head. Touch is a collection of different senses bundled under one label. You have mechanoreceptors in your skin that respond to pressure, vibration, and stretch. You have thermoreceptors that respond to temperature. You have nociceptors that respond to pain. Each type of receptor sends signals to the brain, and the brain integrates them into a unified sense of touch. But the sensations are constructed. Heat is not a thing that flows into your skin. Heat is molecular motion. Fast-moving molecules bump into your skin and trigger thermoreceptors. The warmth you feel is your brain's interpretation of that signal. Cold is the absence of heat, but your brain treats it as a distinct sensation because you have separate receptors for it. Pain is even more complex. Pain signals travel along 2 different pathways. Fast pain, sharp and localized, travels along myelinated nerve fibers and reaches the brain quickly. Slow pain, dull and throbbing, travels along unmyelinated fibers and takes longer. The brain processes these signals and produces the experience of pain. But pain is not out there in the world. There's no pain in a knife blade. The knife causes tissue damage. The damage triggers nociceptors. The nociceptors send signals. Your brain interprets those signals as pain. The pain is generated internally, and here's where it gets uncomfortable. Your brain is not a passive receiver. It's not sitting there waiting for sensory data to arrive and then displaying it on some internal screen. There is no screen. There is no little person inside your head watching the show. Your brain is actively predicting what's going to happen next and comparing those predictions to the incoming data. This is called predictive coding, and it's one of the most important ideas in neuroscience. The basic idea is this: the world is full of patterns. Objects don't randomly teleport. Gravity pulls things down. Sounds usually come from visible sources. Your brain has learnt these patterns through years of experience. When you're walking through a room, your brain is constantly generating predictions. The floor will be solid. The light switch will be where it was yesterday. That chair is not going to suddenly sprout legs and run away. Most of the time, the predictions are correct. When they're correct, the brain doesn't waste energy processing every detail. It just notes that the prediction matched the data and moves on. But when there's a mismatch, when something unexpected happens, the brain pays attention. That mismatch generates a prediction error, and the brain updates its model. You see a chair where you expected empty space, prediction error. You stop before you trip, the brain corrects. This means most of what you experience is not based on current sensory input, it's based on predictions. Your brain is hallucinating your reality, and it's only checking that hallucination against sensory data when something surprising happens. The world you see is a controlled hallucination. When the hallucination matches the data, you perceive a stable, predictable world. When it doesn't, you notice something's off. But you're never seeing the world directly. You're seeing your brain's best guess about what's out there. Illusions expose this process beautifully. Take the Muller-Lyer illusion. Two horizontal lines of the same length. One has arrowheads pointing outward at the ends. The other has arrowheads pointing inward. The line with outward arrowheads looks longer, even though both lines are identical. Your brain interprets the arrowheads as depth cues. The outward arrows suggest a corner receding into the distance, like the far edge of a room. The inward arrows suggest a corner coming toward you, like the near edge of a building. Your brain applies size constancy. Objects farther away look smaller on the retina, so if two objects produce the same retinal image and one is farther away, the distant one must be larger. The arrowheads trick your brain into thinking one line is farther away, so it compensates by making that line look longer. The illusion works even when you know it's an illusion. You can measure the lines, you can confirm they're the same length. Look at them again, and they still look different. Your perception is not under your conscious control, it's automatic. Your brain is applying rules, and those rules can be fooled. Or take the Ames room, a distorted room designed so that when viewed from a specific angle, it looks like a normal rectangular room. But one corner is much farther from the viewer than the other. Put two people of the same height in opposite corners, and one looks like a giant and the other like a child. Your brain assumes the room is rectangular because most rooms are rectangular. Given that assumption, it interprets the difference in retinal image size as a difference in the people's heights. The room is distorted, but your brain doesn't know that. It's making the most reasonable inference based on the available data and its prior expectations. The inference is wrong, but it's the best guess your brain can make. Or the color constancy illusions. You see a photograph of a cube with squares of different colors on its faces. Some squares are in shadow, some are in bright light. You're asked which squares are the same color. You pick two that look obviously different. One looks dark blue, one looks bright white. Then someone edits the image, removes the surrounding context, and places the two squares side by side. They're identical. Pixel for pixel, the exact same shade of gray. Your brain was adjusting for the lighting. It knew one square was in shadow and one was in light, so it compensated. It added color information that wasn't in the image to make the scene make sense. The raw data reaching your retina was gray. The color you saw was a calculation. Your brain is doing this constantly, filling in gaps, making assumptions, smoothing over inconsistencies. You don't see the blood vessels that cross your retina, even though they block light. You don't see the image blur every time you blink, even though your eyelids close several times a minute. You don't notice the saccades, the rapid, jerky movements your eyes make when scanning a scene, even though your eyes are in almost constant motion. Your perception is stable, smooth, continuous. The underlying data is fragmented, incomplete, and constantly interrupted. Your brain is editing the footage in real time and showing you the cleaned-up version, and it has to, because the amount of information hitting your senses every second is overwhelming. Your eyes receive about 10 million bits of information per second, your ears another million, skin another million. That's roughly 10 to the 7th bits per second of raw data. Your conscious awareness processes maybe 50 bits per second. 50. The rest is filtered out. Your brain decides what's important and what's not. It decides what you notice and what you ignore. Most of the world around you, you're not seeing, not because it's not there, but because your brain has decided it's not worth your attention. This filtering is essential. Without it, you'd be paralyzed by information. Every sound, every flicker of light, every texture, all of it hitting you at once, with no prioritization. You wouldn't be able to function. The filter is what lets you focus. But the filter also means your perception of the world is incomplete. You're seeing a tiny curated slice of reality, selected by processes you don't control and mostly aren't aware of. The famous study by Christopher Chabris and Daniel Simons, the invisible gorilla experiment, demonstrates this. Participants watch a video of people passing a basketball. They're asked to count how many times the ball is passed. Halfway through the video, someone in a gorilla suit walks into the frame, beats their chest, and walks off. About half the participants don't see the gorilla. They're so focused on counting passes that their brain filters out the gorilla entirely. It's right there in the video. Impossible to miss if you're not focused on something else. But attention is a spotlight. It illuminates one part of the scene and leaves the rest in darkness. You think you're seeing everything. You're not. You're seeing what your brain has decided to show you. Expectations shape perception even more directly. You hear what you expect to hear. The McGurk effect is a striking example. You watch a video of someone saying the syllable ga while the audio plays the syllable bay. What you hear is da. Your brain is combining the visual information from the person's lips with the auditory information from the sound and producing a compromise. The sensory inputs conflict. Your brain resolves the conflict by generating a perception that splits the difference. You're not hearing the sound that's actually playing. You're hearing what your brain thinks the sound should be based on all available information, or the shepherd tone. An auditory illusion where a series of tones seems to ascend in pitch forever. Each tone is actually a combination of frequencies an octave apart. As the tones play, the higher frequencies fade out and the lower frequencies fade in. Your brain locks onto the rising frequencies and doesn't notice the lower ones cycling back. The result is a sound that seems to climb endlessly without ever getting higher. It's impossible, but your brain buys it because the individual frequency changes follow a pattern that makes sense. Your sense of time is flexible too. Time doesn't flow at a constant rate in your perception. Novel experiences seem to last longer. Familiar experiences compress. The first time you drive to a new place, the trip feels long. The drive back feels shorter. Same distance, same duration, different perception. Your brain is encoding more information on the way there because everything is new. On the way back, it recognizes the route and doesn't bother encoding as much detail. When you recall the trip later, the amount of information stored determines how long the experience feels. More information, longer duration; less information, shorter duration. This is why childhood seems to last forever and adulthood accelerates. When you're a child, Everything is new. You're encoding huge amounts of information. As an adult, your days fall into routines. Your brain stops paying attention to the repetitive details. The years blur together because there's less being stored. Time itself hasn't sped up. Your perception of time has changed because the rate at which you're forming new memories has slowed, and your sense of self, the feeling that there's a continuous you experiencing all of this, that's a construct too. The brain is not a unified system. It's a collection of modules, specialized regions that handle different tasks. Vision is processed in the occipital lobe, language in the left temporal and frontal regions, motor control in the motor cortex, memory formation in the hippocampus, emotional responses in the amygdala. These regions communicate, but they're also somewhat independent. Split-brain patients, people who've had the corpus callosum connecting their brain hemispheres severed to treat epilepsy, show this dramatically. The left hemisphere controls the right side of the body and handles most language. The right hemisphere controls the left side and is better at spatial tasks. In split-brain patients, you can show an image to only the right hemisphere by presenting it in the left visual field. The right hemisphere sees it. The left hemisphere, the one that can talk, doesn't. Ask the patient what they saw. They say nothing. Ask them to point with their left hand, controlled by the right hemisphere, and they point correctly. The right hemisphere saw the image and can act on it, but the left hemisphere, the one producing speech, has no idea. The two halves of the brain are having different experiences, and only one of them can tell you about it. Even in a normal brain, the unity of experience is stitched together after the fact. Different sensory streams are processed at different speeds. Vision takes longer to process than hearing, but you don't experience a lag between seeing someone's lips move and hearing their voice. Your brain synchronizes the signals, adjusting the timestamps so that events that happened at slightly different times feel simultaneous. You experience a constructed now, not the actual sequence of sensory inputs. The color of your thoughts, the inner voice you hear when you read or think, the sense that you're a single coherent self making decisions, all of it is a narrative your brain tells itself. It's a useful narrative. It helps you navigate the world, make plans, interact with other people. But it's not a description of what's actually happening. What's actually happening is electrochemical signals cascading through a network of 86 billion neurons, each connected to thousands of others, producing patterns of activity that somehow give rise to the feeling of being you. How that happens, how objective physical processes in the brain produce subjective experience, is a question we still can't answer. We can map the brain. We can identify which regions are active during specific tasks. We can even stimulate regions and change perception. But we can't explain why any of it feels like anything, why there's an experience at all, why there's something it's like to be you. That question, the hard problem, is the next layer. Because everything we've talked about so far, sensory processing, neural pathways, predictive coding, all of it describes the mechanics of perception. It tells you how your brain builds a model of the world. But it doesn't tell you why that model comes with an inner experience, why the firing of neurons produces the redness of red or the painfulness of pain. The brain is made of atoms. Atoms don't have experiences. Neurons are cells. Cells don't have experiences. Put 86 billion neurons together in the right configuration, and suddenly there's someone home. Suddenly there's a perspective. Suddenly there's a you reading these words and wondering how a lump of cells could possibly produce the sensation of wondering. That gap between the physical processes and the subjective experience is where the explanation runs out. We've described the machinery, we haven't explained the ghost, and that ghost, that inner experience, that sense of what it feels like to be you, is the thing we call consciousness. And it's the single hardest problem in all of science. Let's start with a definition, because consciousness is one of those words everyone uses and no one can quite pin down. In philosophy and neuroscience, consciousness usually refers to subjective experience. The technical term is phenomenal consciousness. It's the what it's likeness of being aware. There's something it's like to see red. There's something it's like to taste chocolate. There's something it's like to feel pain, or hear a symphony, or remember your childhood. That something, that inner qualitative feel, is consciousness. And the individual elements of that experience, the redness of red, the painfulness of pain, the specific taste of coffee, those are called qualia, singular quale, plural qualia. They're the atoms of conscious experience, the building blocks of what it feels like to be you. The problem is that we have no idea how qualia arise from physical processes, none. We can trace the neural pathways, we can watch neurons fire, we can map which brain regions light up when you see red or feel pain. We can describe the entire causal chain, from stimulus to perception. Photons hit your retina. Signals travel along the optic nerve. The visual cortex processes the information. Areas in the temporal lobe integrate the signals with memory and context. All of that is neuroscience. We've got that part mostly figured out. What we don't have is an explanation for why any of that should feel like anything. Why the firing of neurons in your visual cortex produces the experience of redness. Why the activation of nociceptors produces the sensation of pain. You could, in principle, build a complete map of every neuron, every synapse, every chemical signal in the brain, and still not answer the question of why there's someone home, why there's an inner experience at all. This is what philosopher David Chalmers called the hard problem of consciousness. There are easy problems, he said, though easy is relative. The easy problems are things like explaining how the brain integrates information, how it focuses attention, how it differentiates between self and environment, how it accesses internal states and reports on them. Those are mechanistic questions. Hard, yes, but solvable in principle using the tools of neuroscience and cognitive science. You're asking how a system processes information and produces behavior. The hard problem is different. The hard problem is explaining why a system that processes information should have subjective experience, why it should feel like something to be that system. You can describe every physical process in the brain down to the molecular level and still not have touched the question of why those processes are accompanied by an inner life. Some scientists think Chalmers is wrong. They think the hard problem is just a confusion, a trick of language, and once we fully understand the brain's mechanisms, the mystery will dissolve. Consciousness will turn out to be nothing more than information processing of a certain kind, and the feeling that there's something mysterious left over is just our intuition failing to keep up with the science. Others think the hard problem is real and points to something we're missing. A gap in our conceptual framework, maybe even a gap in the physics. The debate has been running for decades and shows no sign of resolution. But let's look at what we do know. We know consciousness is tied to the brain. Damage the brain and you damage consciousness. Specific lesions produce specific deficits. Damage the visual cortex and you lose the ability to see, though your eyes still work. Damage Wernicke's area in the left temporal lobe and you lose the ability to understand language. You can still speak, but what comes out is fluent gibberish. Damage to the prefrontal cortex can change your personality. You're still conscious, but the you that's conscious is different. One of the most famous cases is Phineas Gage, a railroad worker who survived an accident in 1848 when an iron rod was driven through his skull, destroying much of his left frontal lobe. He lived for another 12 years, but people who knew him said he was no longer the same person. Before the accident, he was responsible, hard-working, well-liked. After, he was impulsive, profane, unreliable. The damage didn't eliminate his consciousness. It changed the structure of his inner life. The self is not some immaterial soul floating above the brain. It's a product of brain activity, and when the brain changes, the self changes. Anesthesia works by disrupting brain activity in specific ways. We don't fully understand how all anesthetics work, which is slightly terrifying given how often they're used, but we know they prevent consciousness by interfering with communication between different brain regions. Consciousness seems to require integration. Information has to flow between areas. Disrupt that flow and you lose awareness. During deep anesthesia, your brain is still active, neurons are firing, sensory information is still reaching the cortex, but the signals aren't being integrated. There's no global coordination. And without that coordination, there's no conscious experience. You're not aware of the surgery. You don't form memories. For all practical purposes, you didn't exist during that time. The brain was on, but nobody was home. Sleep is another state where consciousness changes. You're not unconscious during sleep, not completely. You're conscious during dreams. In fact, dreams are one of the strangest forms of consciousness we experience. The brain generates a vivid, immersive world with no external input. You see things, hear things, feel emotions, all of it constructed internally. And most of the time, you don't realize it's a dream. You accept the bizarre logic of the dream world without question. You're flying. Fine. Your childhood home has extra rooms that never existed. Sure. Your dead grandmother is giving you advice. No problem. It's only when you wake up that the absurdity becomes apparent. During the dream, your critical faculties are offline. The prefrontal cortex, the part of the brain involved in logical reasoning and self-monitoring, is less active during REM sleep. You're conscious, but you're not thinking clearly. The dream feels real because the brain systems that would normally question it aren't working. Then there's the question of animal consciousness. Are other animals conscious? It's hard to say because we can't ask them, and even if we could, we'd need a shared language. But the evidence suggests many animals are conscious in at least some sense. Mammals almost certainly are. They have similar brain structures. The cortex, the thalamus, the systems involved in processing sensory information and coordinating behavior. Dogs recognize themselves in mirrors, though not reliably. Dolphins and great apes definitely do. They pass the mirror test, which suggests some level of self-awareness. Crows can plan for the future and use tools. Octopuses, which diverged from the vertebrate line over 500 million years ago, show problem-solving abilities and what looks like playful behavior. They have complex nervous systems, but the structure is completely different from ours. Most of their neurons are in their arms, not their central brain. Does an octopus have a unified conscious experience, or is it more like 8 semi-independent agents coordinating? We have no idea. The question gets harder as you move down the complexity scale. Are fish conscious? Probably, though their experience is likely much simpler than ours. Insects? Maybe. They have nervous systems. They respond to their environment in complex ways. Bees can learn and communicate the location of food sources to other bees through their waggle dance. Does that require consciousness, or is it just automatic behavior? We don't know. At some point, as systems get simpler, consciousness presumably fades out. A bacterium is not conscious. A single neuron is not conscious. But where's the line? Is there even a line? Or is consciousness a spectrum? Does it appear gradually as systems become more complex? Or is there a threshold where it suddenly switches on? These are open questions, which brings us to the theories. Because neuroscience and philosophy have not been sitting idle, there are proposals, frameworks, attempts to explain what consciousness is and how it arises. None of them are universally accepted. None of them have solved the hard problem. but they're the best ideas we have. Global workspace theory, developed by cognitive neuroscientist Bernard Baars in the late 80s and refined by others since, is one of the leading frameworks. The basic idea is that the brain has many specialized modules working in parallel, processing sensory information, controlling movement, accessing memory. Most of this processing is unconscious. You're not aware of the individual neurons firing in your visual cortex or the muscle commands being sent to your legs when you walk. But some information gets broadcast to a global workspace, a kind of mental stage where it becomes available to many different systems at once. That globally available information is what you're conscious of. Consciousness, in this view, is the brain talking to itself. It's the information that's been selected for widespread distribution. When you're aware of something, it's because that information has won the competition for access to the global workspace. Everything else, all the processing happening in the background, stays unconscious. Global workspace theory is appealing because it fits with a lot of what we know about attention and awareness. You're only conscious of what you're paying attention to. Attention is the mechanism that selects which information gets broadcast. It also explains why consciousness seems unified even though the brain is made of separate modules. The modules feed information into the workspace, and the workspace creates a coherent picture. But here's the problem. Global workspace theory explains the function of consciousness. It tells you what consciousness does, how it helps the brain coordinate and integrate information. It doesn't explain why that global broadcasting should feel like anything. Why should information being widely available in the brain produce subjective experience? You could imagine a system that does everything global workspace theory describes: broadcasting information, integrating signals, coordinating behavior, and it could do all of that without any inner experience. It could be a philosophical zombie, a system that acts conscious but isn't. Global workspace theory explains the mechanics, but it doesn't touch the hard problem. Integrated information theory, developed by neuroscientist Giulio Tononi, takes a different approach. IIT starts with consciousness and tries to work backward to the physical properties that produce it. The central claim is that consciousness corresponds to integrated information, not just information, but information that's integrated in a specific way. A system is conscious to the degree that it has a high level of integrated information, symbolized by the Greek letter phi. Phi measures how much the system is more than the sum of its parts, how much the whole has causal power that the individual components don't. A thermostat has information. It registers whether the temperature is above or below a threshold, but that information isn't integrated. The thermostat doesn't combine multiple sources of information in a way that creates something new. A brain, on the other hand, integrates information from millions of neurons, and the pattern of activity across the whole network has properties that no individual neuron has. That integration, according to IIT, is what consciousness is. One of the strange implications of IIT is that consciousness is not limited to brains. Any system with the right structure, the right pattern of integrated information, would be conscious. A computer could be conscious if it's built the right way. Even simpler systems might have a tiny amount of consciousness, a low phi value. IIT doesn't say consciousness appears only in complex systems. It says consciousness is a fundamental property, present wherever there's integrated information, and the amount of consciousness scales with the degree of integration. This is a radical claim. It means a thermostat might have a trace of consciousness, so faint it's meaningless, but technically present. It means the universe might be full of micro-consciousnesses, tiny sparks of experience in systems we don't normally think of as aware. Tononi himself has said that according to IIT, even a simple logic gate has a non-zero phi value. It's conscious, barely, in a way we can't relate to, and that doesn't matter for any practical purpose, but the theory demands it. IIT has some appeal because it's mathematically rigorous. Phi is something you can, in principle, calculate. You can take a system, map out its causal structure, and compute how much integrated information it has. Tononi and his collaborators have developed algorithms to do this for small networks, though it becomes computationally intractable for anything as large as a human brain. IIT also makes testable predictions. It predicts, for instance, that the cerebellum, which has more neurons than the rest of the brain combined, should not contribute much to consciousness because the neurons in the cerebellum are organized in a way that doesn't integrate information across the whole structure. Each module works independently. Damage to the cerebellum impairs motor coordination, but it doesn't seem to impair consciousness. That fits IIT's predictions. But IIT has problems. One is that it's not clear Phi actually measures what we mean by consciousness. You can compute Phi for a system, but does a high Phi value really correspond to what it feels like to be that system? The theory doesn't explain qualia. It doesn't explain why integrated information should produce the redness of red or the painfulness of pain. It's associating consciousness with a mathematical property, but the association feels arbitrary. Why should this particular arrangement of causal relationships feel like something? IIT gives you a structure, but it doesn't close the explanatory gap. Another problem is that IIT leads to some very counterintuitive conclusions. If integrated information is all that matters, then you could have two identical systems, say two brains in identical states, and if one of them is slightly more integrated, it would be more conscious. But from the outside, they'd be indistinguishable. They'd behave the same way, report the same experiences, and yet one would supposedly have a richer inner life. That's hard to test and harder to accept. IIT also implies that consciousness can't be duplicated. If you copied a brain atom by atom, IIT says the copy wouldn't have the same consciousness as the original because the identity of a conscious system depends on its specific physical instantiation. The pattern matters, not just the structure. That might be true, but it's a strange consequence, and it makes consciousness something fundamentally different from other physical properties. Then there's panpsychism, which is less a theory than a family of ideas. Panpsychism is the view that consciousness is a fundamental feature of the universe, present at all levels, not just in brains, not just in complex systems, but in everything. Electrons might have a trace of experience, photons might have a perspective. Every particle, every field, every piece of matter might have some primitive form of consciousness. And the consciousness we experience in humans is what you get when those micro-consciousnesses are combined and organized in the right way. This sounds like mysticism, and for most of the 20th century, it was dismissed as unscientific nonsense. But in the last few decades, panpsychism has gained a surprising amount of traction among philosophers and even some scientists. The argument for panpsychism goes something like this. We know consciousness exists because we experience it directly. We also know that the physical world, as described by physics, doesn't include consciousness. Physics describes matter, energy, forces, fields, all of it third-person objective properties. Nothing in the equations of physics corresponds to subjective experience. So either consciousness is something that emerges from physical processes in a way we don't understand, which is the standard materialist view, or consciousness is a fundamental part of reality that physics hasn't accounted for. Panpsychism takes the second route. It says consciousness is not something that appears only in brains. It's woven into the fabric of reality, and brains are just very good at organizing and amplifying it. One version of panpsychism, called cosmopsychism, flips the picture. Instead of saying that tiny particles have tiny bits of consciousness that combine into larger consciousnesses, it says the universe as a whole is conscious, and individual consciousnesses like ours are localized aspects of that universal awareness. We're not separate minds floating in a dead universe, we're ripples in a cosmic mind. This view has roots in Eastern philosophy, in ideas like Brahman in Hinduism or the Tao in Taoism, but it's being explored by contemporary philosophers trying to make sense of the hard problem. The trouble with panpsychism is that it doesn't really solve anything, it just moves the mystery. Okay, particles have proto-consciousness. How do you combine 1 trillion proto-conscious particles into a single unified conscious experience? That's called the combination problem, and nobody has a good answer. If an electron has a perspective, what is it like to be an electron? And if you combine 1 billion electrons with 1 billion protons and 1 billion neutrons, how do their individual perspectives merge into the experience of being a human? If you can't explain that, then panpsychism hasn't explained consciousness. It's just pushed the hard problem down to a more fundamental level. And if you can explain it, if you can show how small bits of consciousness combine into larger ones, then you've basically solved the hard problem and you didn't need panpsychism in the first place. You could just say, complex systems produce consciousness, which is the materialist view. So where does this leave us? We have global workspace theory, which explains the cognitive function of consciousness, but doesn't explain subjective experience. We have integrated information theory, which tries to ground consciousness in a measurable property of systems, but doesn't explain qualia. We have panpsychism, which declares consciousness fundamental, but doesn't explain how it combines or why we should believe it's everywhere. None of these theories have won. None of them have convinced the field. The hard problem remains hard. There are researchers who think we're asking the wrong question. Maybe consciousness doesn't reside anywhere. Maybe it's not a thing that has a location or a mechanism. Maybe it's just what certain kinds of information processing feel like from the inside. The subjective perspective is real, but it's not separate from the physical processes. It's just the first-person view of those processes. When your neurons fire in the right pattern, that firing is your experience. There's no gap between the neural activity and the qualia. They're the same event described in two different ways. One description is objective, third person, the neurons are firing. The other is subjective, first person, I see red. But they're not two separate things. They're two perspectives on one thing. This is a form of dual aspect theory, or neutral monism. The idea that mind and matter are two sides of the same coin. The problem is that this view, while philosophically coherent, doesn't really explain anything either. It just asserts that the gap isn't real, but the gap still feels real. When you experience the redness of red, it doesn't feel like the firing of neurons. It feels like something entirely different. Maybe that's an illusion, but if it is, we'd like to know why the illusion exists and how it's maintained. Some neuroscientists are focused on finding the neural correlates of consciousness, the specific brain activity patterns that are always present when you're conscious and absent when you're not. This is an empirical approach. Instead of trying to explain why consciousness exists, just map where it happens. Christoph Koch and Francis Crick, before Crick died, spent years searching for the NCC, the neural correlates. They identified certain brain regions and certain patterns of neural firing that seemed to be necessary for conscious experience. The thalamus, for instance, plays a critical role. Damage to the thalamus can eliminate consciousness even if the cortex is intact. Gamma oscillations, neural activity in the 30 to 100 Hz range, also seem to be associated with conscious perception. When different brain regions synchronize their activity in the gamma band, you're more likely to be aware of whatever stimulus triggered the synchronization. But finding correlates is not the same as finding an explanation. It's like saying that every time your car moves, the engine is running. True, but knowing that doesn't tell you how the engine works. The neural correlates tell us which brain activity is associated with consciousness. They don't tell us why that activity produces experience. We've got the where and the when. We're still missing the why. And then there's the possibility that we're missing something big, that consciousness requires physics we don't have yet. Roger Penrose, the mathematical physicist, has argued for decades that consciousness can't be explained by classical computation. He thinks quantum mechanics plays a role. Specifically, he and anesthesiologist Stuart Hameroff have proposed that consciousness arises from quantum processes inside microtubules, structural proteins inside neurons. The idea is that quantum superposition and collapse happen in the microtubules, and that's where conscious experience comes from. The brain is not just a classical computer, it's a quantum computer, and consciousness is what quantum coherence feels like. This is a fringe view. Most neuroscientists don't take it seriously because the brain is warm, wet, and noisy, exactly the kind of environment where quantum coherence falls apart almost instantly. Quantum effects require isolation from the environment. The brain is about as far from isolated as you can get. But Penrose and Hameroff argue that biology has found ways to maintain quantum coherence in other systems, like photosynthesis, so maybe it's possible in the brain too. They've even identified specific predictions, things you could test in principle. But the experiments are incredibly difficult, and the theory remains speculative. If Penrose is right, and that's a big if, it would mean consciousness is not something you can simulate on a classical computer. A perfect simulation of a brain running on a conventional computer would not be conscious. It would behave like a conscious system, but there would be no inner experience. Only systems with the right quantum properties could be truly conscious. That would have huge implications for artificial intelligence, for uploading minds, for the entire project of understanding consciousness in physical terms. But right now, there's not enough evidence to decide one way or the other. What's clear is that after decades of research, hundreds of studies, thousands of papers, we're not much closer to solving the hard problem than we were when Chalmers first articulated it. We know more about the brain. We can map its activity in exquisite detail. We can identify which regions do what. We can watch thoughts form in real time using functional MRI. We can even decode some of what people are thinking by analyzing their brain scans. But none of that tells us why any of it feels like anything. We've made progress on the easy problems. The hard problem is still hard. Maybe consciousness is an illusion. Not that you're not conscious, obviously you are, but that the mystery is overblown. Maybe once we fully understand the brain's information processing, the sense that there's something left unexplained will vanish. The qualia will turn out to be nothing more than certain patterns of neural activity, and the feeling that there's something extra, something non-physical, is just our intuition failing to catch up with the reality. Daniel Dennett, the philosopher, has been arguing this for years. He thinks the hard problem is a philosopher's invention, not a real scientific puzzle. Consciousness, he says, is what the brain does. There's no ghost in the machine. There's just the machine, and the ghost is a story the machine tells itself. Maybe he's right. Or maybe the hard problem points to something we're fundamentally missing. A new kind of physics, a different way of thinking about matter and mind, a recognition that subjective experience is as basic to the universe as mass or charge. We don't know, and that not knowing is part of the story. Because here we are, 13.8 billion years after the universe began, 3.8 billion years after life started on Earth, a few 100,000 years after our species emerged, And we're using brains made of atoms to ask how brains made of atoms can ask questions. The universe has folded back on itself. Matter has become aware of matter. And the awareness, the experience, the consciousness is the thing we can't explain. We can describe every step of cosmic and biological evolution that led to this moment. We can trace the path from quarks to qualia. But the leap from objective processes to subjective experience, that gap is still there, staring at us, daring us to solve it. And maybe that's fitting, because if consciousness is what the universe uses to know itself, then the mystery of consciousness is the universe confronting its own nature. We're not outside observers looking at reality. We're part of reality looking at itself. And the fact that we can't fully explain that looking, that experiencing, that being, might mean we're asking reality to do something it can't, to step outside itself and see the whole picture. We're on the inside. We've always been on the inside. And from the inside, some questions might not have answers, not because we're not smart enough, but because the questions are built into the structure of being the thing that's asking. Still, the search continues. New theories, new experiments, new ways of thinking about what it means to be conscious. Because even if we never solve the hard problem, even if subjective experience remains forever mysterious, the attempt to understand it teaches us something. About the brain, about the universe, about the limits of knowledge, and maybe, just maybe, there are other mysteries out there, other aspects of reality we're not even aware we're missing. Things that don't register in our instruments or our theories because we haven't learned to look for them yet. Realities beyond the veil of what we can currently perceive or measure. Hidden layers of existence that are just as real as the consciousness in your head, but just as hard to explain. And here's the uncomfortable truth. Most of the universe is missing, not lost. Not hidden in some distant corner of space we haven't explored yet. Missing in the sense that we know it's there, we can measure its effects, and we have absolutely no idea what it is. The universe you can see, the stars and galaxies and glowing clouds of gas, all of it, every photon that's ever hit a telescope, represents about 5% of what's actually out there. 5%. The remaining 95% is invisible. It doesn't emit light. It doesn't absorb light. It doesn't interact with light in any way we can detect. And yet it's running the show, shaping galaxies, driving the expansion of space itself, determining the fate of everything that exists. The first hint that something was wrong came in the 1930s. An astronomer named Fritz Zwicky was studying the Coma Cluster, a collection of over 1,000 galaxies about 300 million light-years away. He measured how fast the galaxies were moving. Then he calculated how much mass the cluster should contain based on the visible matter, the stars and gas he could see. The numbers didn't match. The galaxies were moving way too fast. If the cluster contained only the mass Zwicky could account for, the galaxies should have flown apart long ago. Gravity wasn't strong enough to hold them together, but they were together, which meant there had to be more mass, a lot more. Mass that wasn't glowing. Mass that wasn't emitting any light. Zwicky called it dark matter, and for decades, almost no one believed him. The problem was that dark matter sounded like a desperate excuse, a fudge factor. We don't understand the observations, so we'll just invent invisible matter to make the math work. It felt unsatisfying. But then in the 1970s, astronomer Vera Rubin found the same problem on a smaller scale. She was measuring rotation curves of spiral galaxies. A rotation curve shows how fast stars are orbiting at different distances from the galactic center. If most of a galaxy's mass is concentrated in the middle, which it should be because that's where most of the stars are, then stars farther out should orbit more slowly, just like planets in the solar system. Mercury orbits the Sun much faster than Neptune because the gravitational pull weakens with distance. Galaxies should work the same way. Stars near the edge should be crawling along compared to stars near the core. They're not. Rubin found that stars at the edge of galaxies are orbiting just as fast as stars closer in. The rotation curves are flat. That shouldn't be possible unless there's a massive amount of matter spread throughout the galaxy, extending far beyond the visible disk. And that matter, whatever it is, has to be dark. It has to be invisible. Because if it were normal matter, stars or gas or dust, we'd see it. We don't. Rubin's results were rock solid. She measured dozens of galaxies. Same result every time. Flat rotation curves. Too much mass. Not enough visible matter. The only explanation was dark matter. Lots of it. By the 1980s, the astronomy community had accepted that dark matter was real. We still don't know what it is. There are candidates, theories. The leading idea is that dark matter is made of particles that interact only through gravity and possibly the weak nuclear force, not electromagnetism. That's why they don't emit or absorb light. These hypothetical particles are called WIMPs, weakly interacting massive particles. The name is not a coincidence. Physicists have a sense of humor. WIMPs would be heavy, maybe 10 to 100 times the mass of a proton, and they'd be everywhere. Billions of them passing through your body every second. You wouldn't feel them because they don't interact with normal matter in any noticeable way. They just pass through like ghosts. Occasionally, very rarely, a WIMP might collide with an atomic nucleus. That collision would release a tiny amount of energy. And if you built a detector sensitive enough, buried deep underground to shield it from cosmic rays and other background noise, you might be able to catch one. Dozens of experiments have tried. The Large Underground Xenon Experiment, LUX, the Enion 1T detector in Italy, the Cryogenic Dark Matter Search. All of them looking for that tiny flicker of energy that would signal a WIMP collision. So far, nothing. No confirmed detections. Either WIMPs don't exist, or they're even harder to detect than we thought. Some researchers are starting to look at other candidates. Axions, for instance, hypothetical particles much lighter than WIMPs, originally proposed to solve a different problem in particle physics. Axions would interact even more weakly than WIMPs, which makes them harder to detect, but also harder to rule out. Then there are primordial black holes that formed in the first fraction of a second after the Big Bang. If enough of them exist, and if they're the right size, they could account for some or all of the dark matter. But observations of gravitational lensing suggest primordial black holes can't be the whole story. Something else is out there. The evidence for dark matter is everywhere once you know where to look. Gravitational lensing is one of the clearest examples. When light from a distant galaxy passes near a massive object, the object's gravity bends the light. Einstein predicted this. We've measured it thousands of times. The amount of bending tells you how much mass is doing the bending. When you point a telescope at a galaxy cluster and measure how much it's bending the light from galaxies behind it, the mass you calculate is always much larger than the mass you see. The cluster is acting like it contains 5 to 10 times more matter than all the visible stars and gas combined. That extra mass is dark matter, and you can map it. By measuring how the background light is distorted, you can create a map of where the dark matter is concentrated. It forms a kind of scaffolding, a cosmic web of filaments and halos that extends across the universe. Galaxies sit in the densest regions. The dark matter got there first, pulled together by gravity, and then normal matter fell into the dark matter's gravitational wells. Without dark matter, galaxies wouldn't have formed. The early universe was too smooth. The tiny density fluctuations left over from inflation wouldn't have grown fast enough. Dark matter, because it doesn't interact with light or radiation, could start clumping together earlier. It gave normal matter a head start, a framework to collapse into. We owe our existence to stuff we can't see. Then there's dark energy, which is even stranger. If dark matter is invisible mass pulling things together, dark energy is invisible something pushing things apart. In the late 1990s, two independent teams of astronomers were studying distant supernovae, trying to measure how much the universe's expansion was slowing down. Everyone expected the expansion to be slowing. Gravity should be pulling everything back together, gradually breaking the outward motion. The question was how fast the breaking was happening. The answer would tell you the universe's ultimate fate. If the expansion was slowing a lot, eventually it would stop and reverse. The universe would collapse in a big crunch. If it was slowing just a little, it would expand forever, but gradually coast to a halt. Somewhere in between, there was a critical density where the universe would expand forever, but just barely. What the teams found was that the expansion wasn't slowing down at all. It was speeding up. Distant supernovae were farther away than they should be if the universe had been expanding at a constant rate. Something was accelerating the expansion. Something with negative pressure, pushing space apart rather than pulling it together. The discovery won the Nobel Prize in 2011. It also broke cosmology, because nobody knew what could cause that. Normal matter and energy, including dark matter, all have positive pressure or no pressure. They pull, they don't push. The only way to get accelerating expansion in general relativity is to add a term called the cosmological constant, a form of energy that's the same everywhere, constant in time, and has negative pressure. Einstein had introduced the cosmological constant in 1917 to keep the universe static, then abandoned it when Hubble showed the universe was expanding. He supposedly called it his biggest blunder. Now it was back, and it wasn't a blunder. It was necessary to explain the observations. The cosmological constant is usually interpreted as vacuum energy. Even empty space, according to quantum field theory, is not truly empty. It's filled with virtual particles popping in and out of existence, fields fluctuating at the quantum level. All of that activity has energy. The vacuum has energy, and if that energy has the right properties, it acts like a cosmological constant. It pushes space apart. Problem is, when you try to calculate how much vacuum energy there should be based on quantum field theory, you get an answer that's about 10 to the power of 120 times larger than what we observe. That's not a small discrepancy. That's the worst prediction in the history of physics, off by 120 orders of magnitude. Something is clearly wrong with the calculation, but nobody knows what. We know vacuum energy exists. We've measured it in the lab through effects like the Casimir force. We just don't know why it's so much smaller in the universe than theory predicts, so we call it dark energy and admit we're clueless. Dark energy makes up about 68% of the universe's total energy content. Dark matter is about 27%. Normal matter, everything we can see and touch and measure directly, is less than 5%. We're living in a universe where 95% of the content is completely unknown. We've named the missing pieces, we've measured their effects, we have no idea what they actually are. This should bother you more than it probably does. We've mapped the cosmic microwave background to incredible precision. We've detected gravitational waves from colliding black holes over 1 billion light-years away. We've photographed the event horizon of a black hole in another galaxy. And we can't tell you what most of the universe is made of. It's not that the universe is hiding things in distant corners we can't reach. The dark matter is right here, right now. It's in this room. Particles of dark matter are passing through you constantly, trillions of them every second. We just can't detect them because they don't interact with normal matter in any way our instruments can measure. They're ghosts, real ghosts, with mass and gravity, but ghosts nonetheless. And it gets weirder. Because if inflation happened the way cosmologists think it did, if the universe really did undergo that absurdly fast expansion in the first fraction of a second, then inflation probably didn't stop everywhere at once. Most models of inflation are eternal. Once inflation starts, it keeps going in most regions of space. Some regions stop inflating and become universes like ours, but other regions keep inflating, and within those regions, more regions stop and more keep going. It's a runaway process. An infinite fractal of bubble universes, each with potentially different physical laws, different constants of nature, different numbers of dimensions. This is the multiverse, not science fiction, a direct consequence of taking inflation seriously. In some of those other universes, the cosmological constant might be larger, way larger. Space would be tearing itself apart so fast that matter couldn't clump into galaxies or stars. No structure, no life. In others, the constant might be smaller or negative, causing the universe to collapse almost immediately. In others, the strength of the electromagnetic force might be different. Atoms might not form, chemistry might not work. The multiverse, if it exists, is mostly hostile to life. We live in one of the rare bubbles where the constants happen to land in a range that allows complexity. This is sometimes called the anthropic principle. The constants are what they are, because if they were different, we wouldn't be here to measure them. It's a selection effect. You only observe the universe capable of producing observers. The trouble with the multiverse is that it's almost impossible to test. If other universes are causally disconnected from ours, if no information can pass between them, then by definition we can't observe them. Some physicists hate the idea for exactly that reason. It's not science if it's not testable. Others argue that the multiverse is a prediction of inflation, and inflation is testable. We've tested it. The cosmic microwave background fits the predictions. If the theory that explains the data also predicts a multiverse, you can't just ignore the multiverse because it's inconvenient. The equations don't care whether you like the implications. There's also the possibility that we're missing entire dimensions. String theory, one of the leading attempts to unify quantum mechanics and general relativity, requires extra spatial dimensions, not just the three we're familiar with. Depending on the version of the theory, there could be 6 or 7 extra dimensions, maybe more. We don't see them because they're compactified, curled up into shapes so small that we can't detect them. Imagine a garden hose. From far away, it looks one-dimensional. A line. Get closer and you see it's actually a cylinder. There's a second dimension, the circular dimension around the hose, but it's hidden at large scales. String theory says space might be like that. 3 large dimensions we move through freely, and several tiny dimensions curled up at every point in space. Particles and forces are actually vibrations of tiny strings moving through all the dimensions, and the way the strings vibrate in the extra dimensions determines what kind of particle they appear to be in our 3-dimensional slice. String theory is beautiful mathematically. It's the only framework that successfully combines quantum mechanics and general relativity without producing infinities, but it's also incredibly hard to test. The extra dimensions, if they exist, are thought to be on the order of the Planck length, about 10 to the negative 35 meters. That's 20 orders of magnitude smaller than a proton. We can't probe that scale with current technology. We probably never will. Some versions of string theory predict effects we could detect, like mini black holes forming in particle accelerators, but the Large Hadron Collider has been running for years and hasn't seen anything like that. String theory remains a hypothesis, a compelling one, mathematically elegant, but still unproven. Then there's the question of whether space and time are even fundamental. Loop quantum gravity. Another approach to quantum gravity suggests space-time is made of discrete chunks. tiny loops of space woven together into a network. Space isn't continuous, it's granular. At the Planck scale, space has a structure, like pixels on a screen. Zoom in far enough, and the smooth fabric of space-time dissolves into something more like a foam. If that's true, the equations of general relativity are an approximation, valid at large scales, but breaking down at the smallest distances. And if space-time is emergent, built from something more fundamental, then maybe other aspects of reality are emergent too. Maybe the dimensions we perceive, the forces we measure, the particles we detect, all of it could be a kind of projection from a deeper underlying structure we haven't figured out yet. The holographic principle is another strange idea that's gained traction. It comes from studying black holes. When you throw something into a black hole, the information about that object seems to vanish. But quantum mechanics says information can't be destroyed. It has to be preserved somewhere. Stephen Hawking spent years wrestling with this paradox. The resolution, proposed by physicists like Gerard Hooft and Leonard Susskind, is that the information isn't inside the black hole. It's encoded on the event horizon. The two-dimensional surface surrounding the black hole contains all the information about the three-dimensional volume inside. The interior is a hologram, a projection from the boundary. If that works for black holes, maybe it works for the universe. Maybe the three-dimensional space we live in is a holographic projection from information encoded on a two-dimensional boundary at the edge of the universe. We think we're moving through 3 dimensions of space, but the fundamental reality is 2-dimensional, and the 3rd dimension is emergent. Illusion is too strong a word. Emergent, derived, not fundamental. None of this has been proven. These are ideas, frameworks, mathematical structures that might describe reality, or might not. The point is that the more we learn, the stranger things get. The universe we can see and measure directly is a tiny sliver of what's out there. Dark matter is real. We've measured it. We don't know what it is. Dark energy is real. We've measured it. We don't know what it is. The multiverse might be real. We can't measure it. We don't know if we ever will. Extra dimensions might exist. We can't see them. String theory might be the right description of reality, or it might be a beautiful dead end. Space-time might be emergent. The universe might be a hologram. Consciousness might be quantum, or none of that might be true. We're guessing. Educated guessing, based on math and data and decades of work, but still guessing. And here's the thing. We're not equipped to perceive most of reality. Your eyes detect a narrow slice of the electromagnetic spectrum, wavelengths between about 400 and 700 nanometers. That's visible light. The spectrum extends from radio waves kilometers long to gamma rays smaller than atomic nuclei. You see none of it. Ultraviolet radiation is invisible to you, though some animals can see it. Infrared is invisible. X-rays pass through you constantly. You don't feel them. Your ears detect sound waves between about 20 Hz and 20,000 Hz. Frequencies below that, infrasound, you can't hear. Frequencies above, ultrasound, same thing. Elephants communicate using infrasound. Bats navigate using ultrasound. You're deaf to both. Your senses are filters, tuned by evolution to detect the narrow range of stimuli that mattered for survival. You didn't need to see X-rays to avoid predators or find food. You didn't need to hear ultrasound to reproduce, so you don't. Your perception of reality is a thin slice, carefully curated, and you've been walking around your whole life assuming that slice is the whole picture. It's not. Most of the universe is invisible to you, not hidden, not distant. Invisible because your biology didn't bother building sensors for it. We've extended our senses with technology. Telescopes see wavelengths we can't. Radio telescopes detect waves kilometers long. X-ray telescopes catch high-energy photons from black holes and neutron stars. Gravitational wave detectors sense ripples in space-time too faint for any mechanical sensor to catch. But even with all that, we're still limited. We can only detect what interacts with the instruments we've built. Dark matter doesn't interact with light, so no telescope, no matter how sensitive, will ever see it directly. We infer its existence from gravity, from the way it bends light, the way it holds galaxies together, the way it shaped the early universe. But the particles themselves, if they're particles, remain invisible, and there might be other things out there we haven't even imagined. Forces we can't measure because they don't affect normal matter in any way we've thought to test. Particles that exist in the extra dimensions of string theory, unable to interact with our three-dimensional slice. Maybe entire ecosystems of dark matter structures, invisible galaxies made of particles that don't emit light, don't absorb light, and pass through normal matter like it's not there. We wouldn't know. We couldn't know unless we built a detector that happened to be sensitive to whatever those structures are made of. And we can't build a detector for something we don't know exists. It's a catch-22. You need a theory to know what to look for. You need data to build a theory. But you can't get the data if you don't have the instrument. And you don't build the instrument if you don't have the theory. This is why science progresses slowly, why breakthroughs are rare. Most of the time, we're stumbling around in the dark, trying things, measuring carefully, hoping we get lucky, and occasionally we do. Someone notices an anomaly, a signal that doesn't fit, a galaxy rotating too fast, a supernova too far away, a faint hiss from every direction in the sky. And that anomaly opens a door. It shows us something we weren't expecting, something that doesn't fit the current model. And then the hard work begins, figuring out what the anomaly means, building new theories, testing predictions, arguing, publishing, revising. Until finally, maybe, you have a new picture that makes sense of the old data and the new. The picture gets a little bigger, a little more complete, and then someone finds another anomaly, and the process starts again. We like to think we're close to understanding everything. We've mapped the genome, we've detected gravitational waves, we've photographed black holes. Surely we're almost done. We're not even close. 95% of the universe is made of stuff we can't identify. The theory that describes the other 5%, the standard model of particle physics, is incomplete. It doesn't include gravity. It doesn't explain why neutrinos have mass. It doesn't explain the matter-antimatter asymmetry. It doesn't explain dark matter or dark energy. We're missing huge pieces, and every time we solve one problem, we uncover 3 more. Maybe that's just how it is. Maybe reality has layers, and every time we peel one back, there's another underneath. Atoms gave way to protons and neutrons. Protons and neutrons gave way to quarks. Quarks might be made of strings. Strings might be vibrations in a higher dimensional space. That space might be emergent from something else. There's no guarantee we'll ever reach the bottom. There might not be a bottom. The universe might be turtles all the way down. Or maybe we're asking the wrong questions. Maybe the framework we're using, the idea that reality is made of objects with properties existing in space and time, maybe that framework is an approximation too, useful at the scales we operate at, but fundamentally wrong at the deepest levels. Quantum mechanics already hints at this. Particles don't have definite properties until measured. Space and time are relative. The observer affects the system. Reality seems to depend on perspective in ways we still don't fully understand. And if the basic categories we use to describe the world, objects, space, time, causality, if those are approximations rather than fundamental features, then we're trying to solve a puzzle using the wrong language. The pieces won't fit because the pieces are illusions. The real structure is something else entirely. This should be humbling. but it's also exhilarating, because it means there's more to discover. The universe is not a solved problem, it's an open question, and the fact that we can ask the question, that we can build instruments and gather data and test theories and slowly, painstakingly figure out what's real and what isn't, that's extraordinary. We're matter that's learned to study matter. We're the universe investigating itself. And the more we look, the stranger it gets. Dark matter, dark energy, extra dimensions, multiverses, holographic projections, quantum foam. Every answer raises new questions. Every solved mystery reveals deeper mysteries underneath. And maybe that's the point. Maybe the universe isn't supposed to be fully understood. Maybe the search is the thing. The process of looking, questioning, testing, revising, the slow expansion of knowledge into the unknown. We'll never see the whole picture. We're stuck inside it. Limited by our biology, our instruments, our conceptual frameworks. But we keep looking. We build better telescopes. We design cleverer experiments. We think harder about what the data means. And piece by piece, the picture gets clearer. Not complete, never complete, but clearer. Because knowing that 95% of the universe is invisible doesn't mean we stop looking. It means we look harder. We invent new ways to detect what we can't see. We follow the clues, the bent light, the fast-rotating galaxies, the accelerating expansion. Each clue points to something real, even if we can't touch it or see it directly. Dark matter is out there. Dark energy is out there. And if the multiverse exists, if extra dimensions are real, if space-time is a hologram, we'll find evidence eventually. Or we won't. But the trying matters. The search itself matters, because the alternative is to shrug and say the universe is whatever it looks like and stop asking questions. And that's not what we do. That's not what curious matter does. Curious matter looks at the shadows, measures the shapes, and figures out what's casting them, even if the thing casting the shadow is invisible, even if it's made of something we've never encountered, even if it exists in dimensions we can't perceive. We'll find a way. We always have. And in the meantime, we live in the 5%, the visible universe, the part we can touch and measure and understand, at least partially. And even that 5% is filled with wonders, stars being born, black holes colliding, galaxies dancing across billions of years, chemistry building complexity, life emerging, consciousness arising. All of it happening in a universe that's mostly invisible, mostly unknown, and yet somehow, against all odds, capable of producing beings who can look up at the night sky and ask what it all means. So what does it mean? That's the question we've been circling for 13.8 billion years of cosmic history and about 7,000 words of narration. What does any of this actually tell us about reality, about what exists, about what's real and what isn't? And the answer, unsatisfying as it might be, is that reality is far stranger than we ever imagined, and we're only just beginning to understand how strange it really is. Let's take stock of where we've been. We started with the universe itself, born from a singularity 13.8 billion years ago in an event so violent and so incomprehensibly fast that it created space and time themselves. Not in space and time, the entire framework of existence. From that beginning, a hot, dense fog of the simplest particles, the universe expanded and cooled. Gravity did its slow, patient work. Stars ignited. Elements were forged in stellar furnaces and scattered across space in supernova explosions. Planets formed from the debris. On at least one of those planets, chemistry crossed a threshold and became biology. Single cells became complex organisms, nervous systems evolved, brains grew larger. And eventually, one species on one unremarkable planet developed the ability to look back at the entire process and ask how it happened. That's the cosmic story. Atoms to awareness, hydrogen to consciousness. The raw materials were set in the first 3 minutes after the Big Bang. The rest was just assembly. 13.8 billion years of assembly. But the assembly wasn't random. It followed rules, the laws of physics. And those laws, as far as we can tell, are the same everywhere. The speed of light is constant. Gravity works the same way in the Andromeda galaxy as it does in your living room. Quantum mechanics governs the behavior of electrons here and in a star 10 billion light-years away. The universe runs on rules, and those rules are discoverable. That's what science is, the process of figuring out the rules by carefully watching how the game is played. But here's where it gets complicated. The rules we've discovered don't describe reality directly. They describe our measurements of reality, our observations, the data that reaches our instruments. And as we've seen, the act of measuring changes what you're measuring. In the quantum world, observation collapses superpositions. The electron doesn't have a position until you measure it. The photon isn't a wave or a particle until you set up an experiment that forces it to be one or the other. Reality at the smallest scales is not a collection of objects with definite properties waiting to be discovered. It's a set of probabilities that crystallize into definite outcomes when something interacts with them. The universe, at its most fundamental level, is not made of things. It's made of possibilities, and the possibilities become actualities through interaction. That should make you uncomfortable. It means the universe you experience, the solid, dependable world of chairs and floors and stars, is built on a foundation that's fundamentally uncertain. The solidity is an illusion, not in the sense that it's fake. The chair is real, the floor is real. But their solidity is a statistical average over trillions of quantum events. The electron clouds in your body repelling the electron clouds in the chair, each interaction governed by probabilities, each outcome slightly uncertain. But average it over 10 to the 23rd particles and the uncertainty washes out. The quantum fuzziness disappears into classical predictability. The chair feels solid because the numbers are so large that the probability of all the atoms suddenly doing something weird at the same time is effectively zero. But the weirdness is still there, underneath, running the show. And then there's space-time. Space and time aren't separate. They're not a fixed backdrop, they're part of the show. Mass and energy curve space-time. Curved space-time tells matter how to move. What we call gravity is just objects following the straightest possible paths through a curved landscape. Light bends around massive objects, not because the objects are pulling the light, but because the space the light is traveling through is bent. Time runs at different rates, depending on how fast you're moving and how deep you are in a gravitational well. The universe doesn't have a universal now. Simultaneity is relative. What counts as the present depends on your reference frame. Two events that are simultaneous for you might not be simultaneous for someone moving at a different speed. Reality doesn't have a single timeline. It has a web of interlocking timelines, each valid from its own perspective. So the physical universe, the one we can measure and test and build theories about, is already far weirder than common sense would suggest. Quantum uncertainty, relative time, space that bends and ripples, 95% of the content invisible, dark matter holding galaxies together, dark energy tearing the universe apart, and all of that is before we even get to consciousness. Consciousness is where the story turns inside out. Because everything we've been talking about, the Big Bang, quantum mechanics, space-time curvature, all of it is something you know about through your conscious experience. You've never directly perceived a photon. You've never touched space-time. What you have is sensory data processed by your brain, turned into a model, and presented to your conscious awareness as the experience of seeing or hearing or thinking. The universe you experience is not the universe itself. It's a simulation, a controlled hallucination. Your brain's best guess about what's out there, based on incomplete information and millions of years of evolutionary optimization. And that simulation is convincing. It has to be. If your model of reality was wildly inaccurate, you'd walk off cliffs or fail to notice predators or starve because you couldn't find food. Natural selection tuned your perceptual systems to be useful, not accurate. Useful, there's a difference. Accuracy means your perception matches reality exactly. Usefulness means your perception lets you survive and reproduce. Those two things are not the same. Evolution doesn't care whether you see the world as it truly is. It cares whether you see enough of the world accurately enough to pass on your genes. And sometimes, useful perception means ignoring or distorting aspects of reality that don't matter for survival. Take color. Wavelengths of light are real. Your retina detects them. But the colors you experience, the redness of red, the blueness of blue, those are constructs, qualia, subjective experiences generated by your brain. There's no red in the photon. The photon has a wavelength. Your brain takes that wavelength and produces the sensation of red. And we have no way to know if the red you experience is the same as the red someone else experiences. We use the same word. We agree on which objects are red, but the actual subjective quality of redness might be completely different for each person. There's no way to check. You can't step into someone else's consciousness and compare notes. The same goes for every aspect of perception. Sounds are air pressure waves. The hearing is your brain's interpretation. Pain is tissue damage, triggering nerve signals. The suffering is your brain's response. Your entire experienced reality is mediated by neural activity. 86 billion neurons firing in patterns, and somehow those patterns produce the feeling of being you. The sense that there's a continuous self experiencing all of this. That self is a construct too, a narrative your brain tells itself to make sense of the constant stream of sensory input and memory and internal states. You feel like a unified being, but the brain is a collection of modules, different regions handling different tasks. The unity is imposed after the fact, stitched together into a coherent story. So what's real? The quantum fields underlying everything. Yes. The particles and forces we've measured. Yes. The space-time they move through. Yes. But also the subjective experience you're having right now. Yes. That's real too. Just as real as the atoms. Maybe more real, because the atoms are something you infer from experiments and theory, but the experience is something you know directly. You can doubt whether electrons exist. Philosophers have, but you can't doubt that you're having an experience. Descartes nailed that one. I think, therefore I am. The one thing you can be absolutely certain of is that there's a thinker, that there's an experiencer. Whether that experiencer is a soul or a pattern of neural activity or something else entirely, the experience itself is undeniable. This creates a puzzle. Science is incredibly good at describing objective reality, the third-person view, the measurements everyone can agree on, the mass of an electron, the speed of light, the age of the universe. Those are facts, publicly verifiable facts, but science has made almost no progress on subjective reality. The first-person view, what it feels like to be you, why there's something it's like to see red, or feel pain, or remember your childhood. We can describe the neural correlates. We can map which brain regions are active. We can even predict some aspects of your experience based on brain scans. But we can't explain why any of those physical processes should produce an inner life. That gap, the hard problem, is still wide open, and this matters because it means our understanding of reality is incomplete in a very fundamental way. We've mapped the universe from the Big Bang to today. We've described the forces and particles. We've measured the expansion rate and the matter content. We've traced the path from hydrogen to galaxies to planets to life to consciousness. But we can't explain why the endpoint of that process, the conscious being reading these words, has an inner experience. We can't explain why you're not a philosophical zombie, a system that behaves exactly like a conscious being but has no inner life. We know you're not a zombie because you experience things, but we can't say why. The physical story is incomplete without the experiential story. And right now, we have no way to connect them. Some people find this gap frightening. It suggests there might be limits to what science can explain, aspects of reality that will forever remain mysterious. Others find it exciting. It means there's still work to do, deep fundamental work. Maybe we need new physics. Maybe we need a new way of thinking about what it means for something to exist. Maybe consciousness will turn out to be a fundamental feature of the universe, like mass or charge, and we'll need to expand our theories to include it. Or maybe the gap will dissolve once we fully understand the brain. Maybe subjective experience is just what certain kinds of information processing feel like from the inside, and the mystery is only a mystery because we're looking at it the wrong way. Either way, the fact that we're asking the question is extraordinary. We're matter that has organized itself into a configuration capable of wondering about its own existence. The universe has been running for 13.8 billion years. For most of that time, nothing was asking questions. There were no questions to ask, just particles interacting according to physical laws, gravity pulling matter together, stars igniting, galaxies forming, chemistry happening. And then, sometime in the last few 100,000 years, on a rocky planet orbiting an average star in an unremarkable galaxy, a lineage of organisms developed nervous systems complex enough to model their environment, to plan, to remember, to communicate, to wonder. We are the universe's way of knowing itself, and the knowledge we've gained is staggering. We know the universe is 13.8 billion years old. We know it started in a hot, dense state and has been expanding ever since. We know the expansion is accelerating. We know stars forge heavy elements. We know planets form from the debris. We know life can emerge from chemistry. We know consciousness arises from brain activity. We know quantum mechanics governs the small. We know general relativity governs the large. We know the universe is mostly invisible. We know we don't know what most of it is made of. And we know our perception of reality is a construct, a useful fiction built by evolution to help us navigate the world. That last part is crucial, because it means the reality you experience every day, the one that feels obvious and undeniable, is not the whole story. It's not even close. You're seeing a curated slice, a user interface. Evolution didn't build your senses to show you the truth. It built them to show you what you need to survive, and most of the universe, it turns out, you don't need. You don't need to see X-rays or hear ultrasound or detect dark matter particles, so you don't. Your interface hides the complexity. It shows you objects with colors and shapes and sounds. It gives you a sense of space and time. It creates the illusion of solidity and continuity, and it works beautifully. The interface is so good that most people never realize it's an interface. They think they're seeing reality directly. They're not. Science is the tool we use to look behind the interface, to peek at the code, to figure out what's actually running the simulation. And what we've found is that the underlying reality is nothing like the interface suggests. Solid objects are mostly empty space. Colors don't exist outside your head. Time is relative. Particles are probability waves. Space bends. And most of the universe is made of stuff we can't see. The more we look, the stranger it gets. And there's no reason to think we've reached the end. Every layer we peel back reveals another layer underneath. Atoms are made of particles. Particles might be made of strings. Strings might be vibrations in a higher dimensional space. That space might be emergent from something else. The rabbit hole goes deep, maybe infinitely deep. And yet, for all the strangeness, for all the uncertainty, for all the gaps in our knowledge, we've made progress, real progress. We've gone from thinking the Earth was the center of the universe to knowing it's a tiny rock orbiting an average star in one of hundreds of billions of galaxies. We've gone from thinking matter was continuous to discovering it's made of discrete particles. We've gone from Newtonian mechanics to relativity and quantum mechanics. We've measured the cosmic microwave background. We've detected gravitational waves. We've photographed black holes. We've sequenced the human genome. We've built computers that can simulate the evolution of galaxies. Each generation knows more than the last. The picture gets clearer, not complete, not perfect, but clearer. And the picture we have, incomplete as it is awe-inspiring. The universe is vast, over 90 billion light-years across, in the observable region alone, possibly infinite beyond that. It contains hundreds of billions of galaxies, each with hundreds of billions of stars, trillions of planets. And on at least one of those planets, matter has become aware of itself. That's us. We're the universe looking back at its own history, figuring out where we came from, how we got here, what we're made of, and the answers, every time we find one, are more interesting than the questions. The atoms in your body were forged in stars that died billions of years ago. The oxygen you breathe, the carbon in your cells, the iron in your blood, all of it came from supernovae. You are literally made of stardust. That's not a metaphor, that's astrophysics. The hydrogen in your body is even older. It's primordial, left over from the Big Bang itself. You're carrying pieces of the early universe inside you right now. And those pieces have been on a journey through space, through stars, through planetary formation, through the origin of life, through billions of years of evolution, through the rise of complex organisms and nervous systems and brains, all of it leading to you. Sitting here, reading this, thinking about it. That should change how you see yourself. You're not separate from the universe, you're part of it, a temporary arrangement of atoms that will eventually disperse and become something else. The carbon in your bones might end up in a tree, or a cloud of interstellar gas, or another person 1,000,000 years from now. The atoms are recycled, the patterns change, but the matter is ancient. You're a brief eddy in the flow of cosmic time, a pattern that holds together for a few decades and then dissolves. And while it lasts, while the pattern is stable, you get to experience things, to think, to wonder, to ask questions. That's a gift, not in any supernatural sense, just in the sense that it's rare. Most of the universe is not conscious. Most matter doesn't get to think about itself. You do, for now. That's worth appreciating. It's also worth being humble about, because everything we know could be wrong. Not likely, but possible. Science doesn't deal in certainties. It deals in models that fit the data, and the data is always incomplete, always subject to revision. The history of science is a history of overturned ideas. Aristotle thought heavier objects fall faster. Newton thought space and time were absolute. Einstein showed they weren't. Quantum mechanics showed the universe is probabilistic at its core. Every generation discovers that the previous generation's understanding was incomplete. There's no reason to think we're the exception. The models we have now, the standard model of particle physics, the lambda CDM model of cosmology, general relativity, quantum field theory, all of them work beautifully within their domains, but they don't fit together. They can't all be the final story. Something deeper, is waiting to be discovered. And that's exciting, because it means the universe still has secrets, big ones, the nature of dark matter, the nature of dark energy, the origin of consciousness, the unification of quantum mechanics and gravity. The reason the constants of nature have the values they do, the question of whether the universe is unique or one of many in a multiverse, all of these are open questions. We have ideas, we have candidate theories, but we don't have answers, not yet. The next generation of scientists will find some of them. They'll build better telescopes, they'll design cleverer experiments, they'll think harder about the data, and they'll push the boundary of knowledge a little further, and the generation after that will do the same. The process doesn't end. There's always more to discover. But here's the thing, the search for objective reality, the attempt to figure out what exists independent of our perceptions, is valuable, essential even, but it's not the only thing that matters, because we don't live in the objective universe. We live in our experience of it, the subjective universe, the one constructed by our brains. And that universe is where meaning happens, where beauty exists, where love and loss and joy and suffering take place. The equations of physics can tell you how a star forms. They can't tell you why a sunset is beautiful. They can describe the neural activity associated with hearing music. They can't capture what it feels like to be moved by a symphony. The objective story is important, but the subjective story is what we actually live. And maybe that's the real lesson. Reality has two faces, the objective and the subjective, the third-person view and the first-person view. Science is our tool for exploring the objective. Art, philosophy, introspection, those are our tools for exploring the subjective. Both are real, both matter, and neither is complete without the other. A universe without consciousness would be a collection of particles obeying laws. Interesting to describe, but meaningless. No one would be there to appreciate it. A consciousness without a universe would have nothing to be conscious of, no structure, no pattern, no input. You need both. The universe provides the stage, consciousness provides the audience. And somehow, in the process, the audience becomes part of the show. We're 13.8 billion years into the story. The universe has gone from a hot, dense state to a cold, expanding one, from simplicity to complexity, from hydrogen clouds to galaxies to stars to planets to life to minds. And those minds have spent the last few thousand years trying to understand the process that created them. We've made extraordinary progress. We've measured the age of the universe to within a few million years. We've mapped the cosmic microwave background. We've detected particles predicted by theory decades before we found them. We've seen light from galaxies so distant it's been traveling for over 13 billion years. We've watched space-time ripple from colliding black holes. We've photographed the shadow of a black hole 55 million light-years away. We've sequenced our own genome. We've built machines that think. We've sent probes beyond the solar system, carrying messages for anyone who might find them. All of that is astonishing. But maybe the most astonishing thing is that we're here to do it. That the universe, against all odds, produced beings capable of asking what the universe is, capable of being awed by it, capable of feeling small and insignificant and yet somehow connected to the whole vast, incomprehensible structure. You are made of atoms that were in stars. Your molecules obey quantum mechanics. Your body moves through space-time. Your brain constructs reality from sensory data. Your consciousness is a mystery we haven't solved. And yet, here you are, thinking about all of it, part of the story and also the storyteller. So what does it all mean? Maybe it doesn't mean anything. Maybe meaning is something we create, not something we discover. Maybe the universe is just doing what physical laws dictate, and we're along for the ride, assigning significance to events that would happen regardless of whether we noticed them. Or maybe meaning is intrinsic. Maybe the fact that we can ask the question is the answer. Maybe consciousness is the universe's way of mattering, of being more than just particles in motion, of becoming aware of itself and, in that awareness, creating something new, something that wasn't there before. Either way, we have this moment, right now. This brief flicker of awareness in the vast, dark expanse. The universe is 13.8 billion years old. You'll be lucky to see 100. That's a rounding error, a blink. But in that blink, you get to experience the universe, to know that it's old, to know that it's vast, to know that you're a tiny part of something unimaginably large. And somehow, that knowledge doesn't make life smaller, it makes it bigger. Because you're not just you, you're the universe experiencing itself. You're the atoms that were forged in stars, scattered across space, pulled together by gravity, organized into cells, shaped by evolution, and given the ability to wonder about the whole process. That's not nothing, that's everything. The search continues, the questions remain. What is dark matter? What is dark energy? How does consciousness arise? Is there life elsewhere? Are we alone? What came before the Big Bang? What will happen in the future? Will the universe expand forever or collapse? Will intelligence survive? Will we ever understand the whole picture? We don't know, but we're looking, we're asking, we're building, we're learning, and every answer, every discovery, every moment of clarity adds to the story. The story of the universe trying to understand itself. The story of reality peeling back its own layers. The story of what actually exists when you strip away the illusions and look at the raw data. And what actually exists, as far as we can tell, is this: a universe born in fire, expanding for 13.8 billion years, filled mostly with invisible matter and energy we can't identify, governed by rules we've only partly decoded, containing at least one planet where chemistry became biology and biology became consciousness. And that consciousness, brief and fragile as it is, has spent the last few thousand years figuring out where it came from. We're not done. We won't be done in our lifetimes. Maybe we'll never be done. But the trying is what makes us human. The refusal to accept easy answers. The insistence on looking deeper. The drive to know, even when knowing is hard. Reality is strange, stranger than we imagined, stranger than we can imagine, but it's also knowable, piece by piece, measurement by measurement, theory by theory. The universe doesn't hide from us. It just requires effort to understand, and we've been putting in that effort for centuries, building on the work of everyone who came before. Standing on the shoulders of giants, as Newton said, though even Newton didn't see the whole picture. No one does. We all see part of it, and together, generation by generation, the picture gets clearer. So look up at the night sky. Those points of light are stars, distant suns, each one potentially surrounded by planets. Each photon that hits your eye has been traveling for years or centuries or millennia. It left a star when that star was younger, crossed the void of space, survived the journey through Earth's atmosphere, and landed on your retina, and your brain took that signal and turned it into the experience of seeing a star. The star is real, the light is real, the experience is real. All of it. The objective and the subjective, the measured and the felt, that's reality. Complex, layered, mostly hidden, but real, and we're part of it. Not outside observers, not separate from the machine. We're inside. We've always been inside. We're made of the same stuff, subject to the same rules, shaped by the same history, and yet somehow we've managed to step back far enough to see the pattern, to trace the thread from the Big Bang to this moment, to understand, at least partially, what we are and where we came from. That's the triumph. Not that we've solved everything, but that we've come this far, that we've looked at the universe, in all its vastness and strangeness, and refused to look away. 13.8 billion years of reality, from quantum foam to consciousness, from nothing to everything, from the smallest scales to the largest, from the simplest atoms to the most complex brains, all of it woven together into a single story, and that story is still being written. By scientists, by philosophers, by anyone who looks up and wonders. The universe gave us the ability to ask questions. The least we can do is keep asking, keep looking, keep trying to understand, because that's what we are. That's what consciousness does. It looks at reality and asks what's real. And sometimes, when we're lucky, reality answers. So here we are, 13.8 billion years after the beginning, sitting on a rock made of exploded stars, using brains built from recycled atoms to ask what any of this means. And the honest answer is, we still don't know. Not completely, not even close. We've mapped the journey from quantum foam to galaxies to consciousness, and at every step, the universe turned out to be stranger than we thought, weirder than we expected, more layered, more hidden, more uncertain than any model predicted. The things we can see and touch make up 5% of what exists. The rest is invisible, unknown, operating by rules we're still guessing at. But maybe that's the point. Maybe the universe isn't supposed to hand us answers. Maybe reality is something you have to work for, piece by piece, generation after generation, always knowing the picture will never be complete. We'll never see it all. We're on the inside, part of the system trying to understand itself. And the fact that we've gotten this far, that we've traced the thread from the Big Bang to this moment, that we've learnt to read the cosmic microwave background like a history book and decode the language of quantum fields, that alone is extraordinary. You are not separate from this story. You're made of it. The atoms in your body are older than the Earth. The patterns firing in your brain right now are the universe thinking about itself. Consciousness is not something that happened to the universe. It's something the universe did. And the mystery, the deep, uncomfortable mystery that still won't go away, is why any of it feels like something, why there's an inside at all. We've come 13.8 billion years to ask that question. The answer, if there is one, is still ahead. And the search continues. Keep asking, because every careful question extends the map, and every discovery reveals another horizon beyond it.